At the center of our Milky Way galaxy, hidden behind clouds of dust and stars, lies something we cannot see with our eyes. This mysterious object has the mass of millions of suns. It is called Sagittarius A star, and it is a supermassive black hole. Unlike the monsters that power distant quasars and active galaxies, Sagittarius A star barely makes a peep. Its silence is misleading. Just beneath the surface, there is a storm of magnetic fields, flares, and extreme gravity that stretches the limits of physics. This is the story of how we discovered it. This is the story of how we photographed the unseeable. This is the story of what this black hole has taught us about the universe. For a long time, even after people began building telescopes and studying the stars with scientific tools, the center of the Milky Way remained hidden. Astronomers could map parts of the sky, track planets, and chart the motion of stars, but something was still in the way. Whenever they turned their instruments toward the thickest part of the Milky Way, toward the constellation Sagittarius, they ran into a wall. It was a wall of light and shadow, of gas and dust, and of stars packed so tightly that they blurred into each other. This area, now known as the galactic bulge, is one of the most crowded regions in the entire Milky Way. It is a huge central swelling made of hundreds of billions of stars. From our vantage point on Earth, it lies in the direction of the galactic center, but seeing through it is not an easy task. In fact, for centuries it was nearly impossible. When people look up at the Milky Way with the naked eye, they see a pale, milky band stretching across the night sky. It looks almost like a faint, ethereal cloud, but that band is not made of cloud or mist. It is made of stars. There are so many stars packed so close together that they blend into a soft, gentle glow. That glow gets brightest near the center of the Milky Way. But along with the brightness, there comes something else: darkness. This darkness is not the absence of stars. It is the presence of dust. All across our galaxy, floating between the stars, are vast clouds of interstellar dust. These clouds are made of tiny microscopic particles. They are bits of carbon, ice, and rock that have been left over from older, long-dead stars, and they are drifting slowly through the emptiness of space. While these particles are incredibly small, they are spread out over such huge distances that they are able to block the light, especially the visible light, which is the kind that our eyes and our early telescopes could see. That is the key to the problem. For most of history, telescopes only worked in the visible light spectrum. They were built like giant mechanical eyes, collecting the light from the stars and focusing it into images. But visible light is very easily blocked. When it tries to pass through a cloud of dust, it gets either scattered or absorbed, and nowhere in the sky is there more of this dust than in the direction of the galactic center. Astronomers would look towards the constellation of Sagittarius and see nothing but confusion. They would see a thick, chaotic mess of stars broken up by dark, ominous streaks that looked like smoke that had been smeared across the sky. The stars that were closer to the Earth were visible, but behind them there was only darkness. The light from the true center of our galaxy simply could not reach us. It was as if someone had drawn a thick, heavy curtain across the very middle of the Milky Way, and the bulge itself only made things worse. Unlike the flat disk of stars that stretches out like a pancake around the rest of the galaxy, the bulge is swollen and round. It is thicker and much denser than the outer regions. The stars in the bulge are packed very closely together, overlapping and shining in all directions at once. But because there are so many of them, and because of all of the dust that is mixed in with them, their light becomes very hard to separate. The signals are there, but they get lost in the overwhelming noise. This is what made the center of our galaxy one of the most mysterious places in the entire sky. People could see the outer arms of the Milky Way, and they could map the stars that were in the nearby regions, but they could not see what lay at the very heart of it all. They did not even know if there was a heart. Was the galaxy spinning around something? Was there a true center at all? Or was it just a loose collection of stars with no fixed point to hold them all together? Some of the early astronomers had believed that the sun was near the center of the Milky Way. When they looked around, they saw stars in every single direction. So they had guessed that we must be somewhere near the middle of it all, but that was only because they could not see past all of the dust. Their view was completely blocked in the direction of the real center, so it had looked to them as if the stars were all evenly spread out. In the 18th and 19th centuries, astronomers like William Herschel had tried to map out the shape of the Milky Way by using star counts. They were simply counting how many stars were visible in the different directions, and they were trying to figure out the structure of the galaxy. But they did not know about the existence of interstellar dust. So when their maps showed more stars in some directions and fewer in others, they had assumed that it meant that the galaxy was shaped unevenly. In truth, the dust was hiding much of what they had needed to see. It was not until the 20th century that things began to change. New kinds of telescopes were being developed, ones that did not just use visible light. Scientists had realized that if they wanted to be able to see through all of the dust, they would need to use forms of light that could pass through it more easily, like infrared and radio waves. These types of light are invisible to our own eyes, but they carry information just like visible light does. And unlike visible light, they are able to travel through the dust without being scattered or absorbed as much. With the new infrared telescopes, astronomers could finally begin to peer into the galactic bulge. They could see the stars that were hidden behind the thick clouds. They could begin to map out the true shape of the center of our galaxy. And with the new radio telescopes, they began to pick up signals that were coming from deep within the galaxy. These were waves of energy that were coming from strange and mysterious sources that had never been seen before. One of the most important of these discoveries came in the 1930s and 40s. Radio astronomers had started to detect a strong signal that was coming from the constellation of Sagittarius. It was not a normal star, and it did not look like anything that was familiar. It was a powerful source of radio waves, and it was coming from the very center of the Milky Way. They called it Sagittarius A. At first, it was just a bright spot in their radio images, and it was buried deep inside the galactic bulge. But over the years, as their instruments had improved, and as the scientists had studied the region more closely, they had begun to realize that there was something very strange that was there. There was something massive, something that was completely invisible, and something that was pulling the stars around it at incredible and unimaginable speeds. But even then, the dust and the gas had made the study of the galactic center incredibly difficult. Astronomers had had to build better and better instruments, and they had had to work from the tops of mountains, from balloons, and eventually from space to be able to get clearer views. The galactic bulge had remained one of the most crowded, chaotic, and complex places in the entire galaxy. What had made it even harder was the fact that the stars in the galactic bulge are moving very fast. They are not just slowly drifting along, they are whipping around the center of the galaxy in tight, fast orbits. Tracking those motions requires an extreme level of precision. You have to watch the same stars for years on end, and you have to take very careful measurements to be able to understand their paths. And it is only then that the patterns begin to appear. All of this, the dust, the density, and the movement, had all combined to keep the truth hidden for most of human history. While the ancient peoples had made up their stories and the early scientists had guessed at its shapes, the real center of the Milky Way had remained completely blocked by its own structure. It had been there all along, hiding behind a glowing, swollen mass of stars and a thick, dense fog of interstellar material. It was only by looking with new kinds of eyes that we could begin to see it for what it really was. In the early 1930s, a young engineer by the name of Karl Jansky was working at the Bell Telephone Laboratories in New Jersey. His job had absolutely nothing to do with the field of astronomy. He was simply trying to solve a problem for the long-distance radio communication. At the time, the technology of radio was growing very fast. Ships, stations, and entire countries were all depending on having clean signals. But there were some strange background noises, a kind of static that could not be explained. Jansky was asked to find out where these noises were coming from. To be able to do this, he built a very strange-looking machine. It was a large rotating antenna. Some people had called it a merry-go-round because it was sitting on a set of wheels and it could be turned to face different parts of the sky. It was designed to be able to pick up radio waves in the shortwave band, which was around 20.5 megahertz. That is a much lower frequency than that of visible light, but it carries some useful information for the purposes of communication. Jansky spent months collecting his data. He found that some of the static was coming from the nearby thunderstorms and that some of it was coming from distant lightning strikes. But there was one particular source of noise that came and went in a very regular pattern about once every 24 hours. At first he had thought that it must be related to the sun in some way, but over time the timing did not match up exactly. It was coming roughly 4 minutes earlier each and every day. That is when he realized that this source was not tied to the rotation of the Earth relative to the Sunday. It was matching the rotation of the Earth relative to the stars. In other words, it was coming from deep space. The direction of the signal was pointing directly toward the center of the Milky Way. This was the very first time that anyone had ever detected radio waves that were coming from outside of our own solar system. It was a complete accident, a side effect of some routine engineering work. Jansky's discovery was the beginning of the field of radio astronomy. At first, the news did not cause a great deal of excitement. Astronomers were still very much focused on their optical telescopes, and very few of them had understood the importance of the radio signals that were coming from space. Jansky himself did not continue with his research into space. Bell Labs had moved on to other projects, and his antenna was eventually dismantled, but his discovery had planted a seed. A few years later, a man by the name of Grote Reber had picked up where Jansky had left off. Reber was a radio engineer and an amateur astronomer. He had read about Jansky's work, and he had decided to build his own radio telescope in his own backyard. He had constructed a large parabolic dish, which was about 9 meters across, and he had begun to scan the sky for radio waves. Reber had confirmed Jansky's results, and he had mapped out the radio sky for the very first time. His maps had shown some strong radio signals that were coming from the same part of the sky. Throughout the 1940s and 50s, more and more scientists had joined the field. Radio astronomy had started to grow. New antennas were being built, and they were larger, more sensitive, and able to cover a wider range of frequencies. These new instruments were revealing a sky that was completely invisible to the human eye. Objects that had looked dark in the visible light were sometimes glowing brightly in the radio waves. The center of the Milky Way, which had once been hidden behind all of that dust, was now beginning to speak in a new and different language. By the 1960s, the radio telescopes had become very powerful tools. Scientists could now study the structure of our galaxy in a great deal of detail. They had detected radio signals from the gas clouds, from the supernova remnants, and even from other galaxies. But one particular spot had remained especially interesting: the strong, compact radio source that was in the direction of Sagittarius. This signal, which had first been noticed by Jansky, was coming from a very specific point in the sky. It was steady, strong, and it was located right at the very heart of the Milky Way. It did not flicker, and it did not spread out across the sky. It was compact, and it was confined to a very small area. That had suggested that it was coming from something that was small, but also incredibly powerful. But even in the 1970s, no one had known exactly what it was. The signal was very strong, but it was not easy to explain. It did not match the patterns of any of the known nebulae. It did not look like a supernova remnant. To be able to learn more, the astronomers had needed to watch how the stars were moving around this invisible point. But this kind of research had taken a great deal of time. The center of the Milky Way is 26,000 light-years away. The stars there are moving very quickly, but not so fast that their orbits can be tracked in just a few days or weeks. In the second half of the 20th century, scientists had begun to build instruments that could detect the infrared light that was coming from space. Some of the earliest of these attempts had been made by using high-altitude balloons and aircraft. The atmosphere of the Earth absorbs a lot of the infrared light before it is able to reach the ground. If you want to be able to study the sky in the infrared, then you need to get above the thickest parts of the atmosphere. One of the key steps in this process was putting the infrared telescopes on the tops of mountains. In places like Mauna Kea in Hawaii or the Atacama Desert in Chile, the air is very dry and thin. That makes it much easier for the infrared light to be able to reach the instruments. From these high points, the astronomers had begun to collect the first clear images of the stars and the gas clouds that were hidden in the center of the Milky Way. Even the early results had been surprising. In the regions that had looked dark in the visible light, the infrared telescopes had revealed entire clusters of stars. The heart of our galaxy was not empty at all. It was full of activity. What had once been a blank patch of the sky was now coming to life. Still, the ground-based telescopes had their limits. The Earth's own heat and its atmosphere had made it very difficult to get clear, uninterrupted data in certain infrared wavelengths. The next step was to go into space. In 1983, NASA had launched the Infrared Astronomical Satellite, or IRAS. It was the very first telescope to map the entire sky in the infrared. Although it was not focused only on the galactic center, it had shown just how much was being hidden in the dusty parts of the sky. Whole regions of space that had seemed to be empty in the optical images had lit up in the infrared, and they were filled with young stars, warm dust, and strange sources of heat. Later, space telescopes, like the Spitzer Space Telescope, which was launched in 2003, would go much deeper, and they would spend years looking into these hidden regions. Spitzer was especially important. With its very sensitive instruments, which were cooled to very low temperatures, it could pick up the faint heat signatures from all across the galaxy. One of its targets was the center of the Milky Way. Using its infrared eyes, Spitzer had seen the stars that were swirling very close to a dense, invisible spot. This point, which was already known from the radio signals as Sagittarius A star, was now under observation in a new and different way. While Spitzer was working from space, the ground-based infrared telescopes were also improving. In Chile, at the European Southern Observatory's Very Large Telescope, a team that was led by Reinhard Genzel had spent years tracking the motion of the stars that were near the galactic center. At the same time in Hawaii, another team that was led by Andrea Ghez had used the Keck Observatory to do the very same thing. They had used some advanced infrared cameras to be able to pierce through the dust and to be able to follow the paths of the individual stars. These were stars that were so close to the black hole that they were completing their orbits in just a few years. These stars, which were called the stars, had become the key to proving what it was that lay at the center of the Milky Way. One of them, which was named S2, is moving in a long, fast orbit that is bringing it extremely close to Sagittarius A star. By watching its path over time, both of the research teams were able to calculate the mass of the object that was pulling on it. The result was stunning. The object had the mass of about 4 million suns, but it was packed into a space that was smaller than our own solar system. It did not emit any light like a star. It was almost certainly a supermassive black hole. None of this would have been possible without the field of infrared astronomy. The dust that was around the galactic core was still blocking all of the visible light. But in the infrared, the story had become very clear. The stars were dancing around an invisible force. The heat was glowing where the eye had seen nothing, and the shape of the galaxy's hidden center was beginning to emerge. With the right kinds of tools, the movements of the stars can be measured down to just a fraction of a second of arc, which is a tiny angle in the sky. But it is enough to be able to reveal some dramatic stories when you are watching something over the course of years or even decades. In the 1990s, a group of astronomers had begun to do just that. One of the teams was being led by Reinhard Genzel, who was working out of the Max Planck Institute in Germany. Another was being led by Andrea Ghez, who was at UCLA in California. Each of these teams was using some powerful ground-based telescopes that were fitted with some advanced imaging systems to be able to peer through the thick dust of the galactic center. Even with the infrared telescopes, the challenge was immense. The atmosphere of the Earth is creating a constant interference, and it is blurring the images and making the stars appear to be shimmering or moving randomly. To be able to deal with this, the astronomers were using a technology that is known as adaptive optics. It was allowing the telescopes to be able to adjust in real time, and it was cancelling out much of the distortion that was being caused by the air above. Near Sagittarius A star, they had found some stars that were moving at incredible speeds. These stars were whipping around a point in space like comets that were flying past a campfire. Some of them were travelling at over 5,000 kilometers per second. That is fast enough to be able to go from the Earth to the Moon in just over a minute. The key breakthrough had come from watching these stars over a long period of time. One in particular, which was known as S2, or sometimes S0-2, had stood out. It was a bright star that was moving in a tight, fast orbit around a completely dark region of space. Over the course of just 16 years, S2 had completed a full loop. No star that was this close to the center had ever been tracked for so long with such a high level of precision. S2 was following an elliptical path, just like the planets do around the Sun. That had meant that it was responding to the force of gravity. From the orbit of S2 and the other nearby stars, the astronomers were able to calculate the mass of whatever it was that was pulling on them. The answer was staggering. Over 4 million times the mass of our own Sun, and it was all packed into a region that was smaller than our own solar system. This had left only one possible explanation: a black hole. And not just any black hole, but a supermassive one. It was the closest evidence that we had ever had of such an object. Black holes had been suspected and theorized for decades, but most of the time they had only been studied indirectly through the X-rays from the distant galaxies or the simulations on the computers. Here, for the very first time, the scientists were watching the stars that were orbiting around real stars that were moving in real time around something that was truly invisible. The evidence had grown stronger with every passing year. More of the stars were being tracked. Some of them had longer orbits. Some of them were even closer than S2. All of them were pointing to the same central object. And even more, the orbits were behaving exactly as had been predicted by Einstein's general theory of relativity. Their paths were showing some subtle changes, some slight shifts in their timing and their direction that could not be explained by Newton's laws alone. This had meant that the gravity that was near Sagittarius A star was not only strong, it was also warping space and time itself. In 2002, Andrea Ghe's team had published the first full orbit of S2. In 2008, Reinhard Genzel's group had followed up with some even more precise measurements. The results were nearly identical. Both of the teams, who were working independently on the opposite sides of the world, had reached the exact same conclusion. There was a massive invisible object at the very center of our galaxy. Its gravitational pull was shaping the motion of the nearby stars. It could be nothing else but a black hole. As the technology had improved, the observations had become even sharper. By the 2010s, the telescopes were capturing the positions of the stars down to 1,000th of a second of arc. That is like measuring the width of a human hair from several kilometers away. And these measurements had kept on confirming what we had already known. Sagittarius A star was real. It was shaping the space that was around it. It was a black hole. And yet, in all of this time, we had still not seen it. Not directly. We had watched the stars as they were moving. We had followed the invisible footprints. But the black hole itself had remained unseen. It would be some time before we would find a way to be able to look even closer. When scientists first began to understand the nature of black holes, they were not just looking at one single type of object. The idea of a black hole is a simple one in theory. It is a region in space where the force of gravity is so strong that nothing, not even light, is able to escape. But the ways in which such objects can form, grow, and behave can be very different. This is why astronomers often talk about the different types or classes of black holes. The one that is at the center of our own galaxy, Sagittarius A star, belongs to the largest known class, which is the supermassive black holes. But it is far from being the only kind. Understanding the others helps to explain just how unusual our own galactic center really is. The smallest of the known black holes are what are known as the stellar mass black holes. These are the remains of the massive stars that have reached the end of their lives in the violent explosions that are known as supernovae. When a star that is several times heavier than our own sun has burned through all of its fuel, it no longer has the energy to be able to push back against the force of gravity. The core of the star collapses, and if the mass is high enough, it will become a black hole. These objects are very small on a cosmic scale, and they are sometimes only a few kilometers across. Yet they are able to hold more mass than our own Sunday. Despite their small size, they can have some very powerful effects on their surroundings, especially if they are able to pull in material from a nearby star, which will form an accretion disk that shines very brightly in the X-rays. These stellar mass black holes are scattered throughout all of the galaxies, including our own, and astronomers have now found dozens of them through the careful observation of such energetic emissions. A step up from these, though they are much harder to find, are the intermediate mass black holes. These range from hundreds to thousands of times the mass of our own Sunday. Their origins are not yet fully understood. Some of the theories have suggested that they could be formed from the merger of multiple different stellar mass black holes inside of the dense star clusters. Others have suggested that they might grow by steadily consuming the gas and the stars over long periods of time. They are very rare in our observations, which is what makes them so interesting. The intermediate mass black holes may be representing a kind of missing link in the growth process that is between the stellar mass and the supermassive black holes. If these mid-sized objects are truly out there in large numbers, then they might be the very seeds that will later grow into the giants that we are seeing at the centers of the galaxies. And then there are the true giants, which are the supermassive black holes. These weigh millions to billions of times the mass of our own Sunday. Sagittarius A star is on the lighter side for this particular class of objects, but even that makes it unimaginably powerful. Unlike the stellar mass black holes which are forming from single stars, the supermassive black holes could not have been formed in one single sudden collapse. They must have built up their mass over a long period of time, and they had possibly begun with the collapse of the enormous clouds of gas in the very early universe, or from the mergers between the smaller black holes and the star clusters. Almost every single large galaxy appears to have one of these giants at its very core, and they are playing a major role in shaping the evolution of their host galaxies. There is also a type of black hole that exists only in theory. These are the primordial black holes. These would have been formed not from the stars, but from the extreme density fluctuations that had occurred in the very early universe, just moments after the Big Bang. The idea is that tiny regions of space could have been so dense that they had collapsed directly into black holes. Some of them would have been no bigger than an asteroid, while others could have potentially been much larger. If they do exist, then they could be scattered everywhere, and they could perhaps even be passing through our own solar system from time to time without ever being detected. Some scientists have even proposed that certain unexplained cosmic phenomena could be the result of such ancient black holes. Another interesting theoretical type is the ultramassive black hole, which is an extension of the supermassive category. These would have masses that would be exceeding 10 billion suns, and a few candidates have already been observed in the centers of some extremely large galaxies. Their sheer size is raising some questions about how fast the black holes can grow and whether there is a natural limit to their mass. Sagittarius A star is firmly in the supermassive category, but it does have some very unique qualities. Compared to the largest of the black holes in the entire universe, it is relatively quiet. Many of the supermassive black holes are very active, and they are consuming huge amounts of material and producing some blazing jets of energy that can be seen across the cosmic distances. Our own galactic center is currently in a very low activity phase, and it is only feeding occasionally and producing some brief flares in the radio infrared and X-ray wavelengths. This quietness is what makes it harder to study in some ways because it does not have the bright, obvious emissions that the active galactic nuclei are producing. Yet it also makes it an ideal laboratory for studying the black hole itself without all of the interference from the chaos of the extreme feeding events. By comparing Sagittarius A star to the other black holes, scientists are able to gain some perspective on its role in our own galaxy. The stellar mass black holes might be more common, but their influence is very local. They are only affecting their own immediate surroundings. The intermediate mass black holes could be bridging the gap, but they are very rare in our detections, and their origin is very uncertain. The supermassive black holes are what are shaping the entire galaxies, and they are holding them together with their immense gravity and influencing the movement of the stars and the gas that are far beyond their own event horizons. And if the primordial black holes do exist, then they could be providing us with some clues about the very earliest moments of the universe. Although finding them would be far more difficult than tracking the massive object that is at the center of our own Milky Way. All of these different types of black holes, from the smallest of the stellar remnants to the most colossal of the supermassives, are all sharing one unifying trait. Their gravity is absolute. Once anything crosses their event horizon, it is gone from the observable universe forever. Yet their differences are painting a picture of the cosmic diversity that exists within the category of the black hole. This diversity is why the astronomers are not just simply studying Sagittarius A star in isolation, but they are instead placing it in the larger context of the research into black holes. It is helping us to see what is typical and what is unusual about our own galactic center. From our position on the Earth inside of the Milky Way, we cannot look down at our own galaxy from above. We are stuck inside of it, and we are surrounded on all sides. So to be able to talk about the different regions of our galaxy, astronomers are using the constellations as a kind of directional signpost. When they are saying that something is in the constellation of Sagittarius, they are meaning that it is lying in the sky within the area of that particular constellation. It does not mean that the object is a part of that constellation, just that it is in the same region of the sky. When the astronomers had looked closer in the direction of Sagittarius with their radio telescopes, they had realized that they were seeing a cluster of different sources and that they were all located near the center of the Milky Way. To be able to keep track of all of these different signals, they had needed to give them names. The astronomer Bruce Ballack and his colleague Robert Brown were studying the central radio source in the early 1970s, and they were using some high-resolution radio imaging. They were zeroing in on a very compact point that was at the very heart of this group of sources. They had called the whole group Sagittarius A, since it was the first major radio source that had been found in that particular region. This was following the naming tradition that was being used in the field of radio astronomy at the time. The A had stood for the first discovered object in the constellation of Sagittarius that was giving off radio waves. If more of these sources were to be found nearby, then they would be called Sagittarius B, Sagittarius C, and so on. Within Sagittarius, Ballack and Brown had identified a point that had looked, as far as their equipment could tell, like a kind of central engine and perhaps even the very core of the entire Milky Way. That is when they had given it its very unusual name, Sagittarius A star, which is written with an asterisk at the end. At the time, Ballack and Brown were using a coding style that had been borrowed from the field of atomic physics. In those fields, the asterisk was sometimes added to a name to be able to indicate an excited state, which was a version of an atom or a particle that had more energy than was usual. It was not a formal naming rule in the field of astronomy, but it had felt right to them. Sagittarius A star was more intense, more concentrated, and more mysterious than the rest of Sagittarius A. The asterisk was their way of pointing that out. The name had stuck. In the years that had followed, as the astronomers from all across the world had focused more and more on this strange and mysterious spot at the center of the Milky Way, the name Sagittarius A star had become the standard. It had shown up in the papers, the telescope logs, and the research reports. Even as the technology had advanced, and as the scientists had grown more and more confident that this object was a black hole that was millions of times more massive than our own sun, the name had remained. In a way, it is a bit ironic. The asterisk, which is read aloud as star, is sitting at the end of the name for an object that is not a star at all. Sagittarius A star does not give off its own light in the usual way. It pulls light in, it bends space, it swallows anything that gets too close. And yet the name is giving this invisible thing a place on the map. The field of astronomy is full of these kinds of names. Some of them, like Betelgeuse or Vega, are coming from the ancient languages. Others, like M31 or NGC 2392, are catalogue numbers, and they are codes that were given by the people who were trying to list thousands of different objects without having to use any poetic titles. When scientists are discovering something that is new, especially something that is not visible to the naked eye, they will often fall back on a mixture of tradition, convenience, and a little bit of creativity. The radio sources, for example, are usually named by their location and their order of discovery. The pulsars, which are the spinning neutron stars that are sending out the regular radio pulses, are often labelled with their coordinates like PSRB 1000, 919 plus 21, and so on. Sometimes the names are beautiful, and sometimes they are just practical. But in every single case, they are helping the scientists to be able to keep track of what it is that they are studying. In the case of Sagittarius A star, the name is doing more than just marking a spot on the sky. The name may be a simple one, but that one small mark, a single asterisk, is carrying the weight of an entire galaxy. Almost every single galaxy, no matter its size or its shape, seems to have a giant black hole at its very core. The same kinds of massive gravitational anchors are appearing at the heart of the spiral galaxies, the elliptical galaxies, and even many of the irregular galaxies. Some of them are bigger than Sagittarius A star, and some of them are far smaller. But the common thread is very clear. This seems to be a rule of the universe. The first hints of this had come from the galaxies where the central region was unusually bright. These active galactic nuclei were giving off enormous amounts of radiation. They were so powerful that no ordinary cluster of stars could possibly explain them. The most convincing explanation was that a supermassive black hole was feeding on the gas and the dust, and it was releasing a tremendous amount of energy as the material was spiraling inward. This same reasoning had been applied to the quasars, which are the brilliant beacons that are seen billions of light years away, and which are now understood to be powered by the black holes that are weighing millions or even billions, 2 times the mass of our own Sunday. Once the astronomers had had the right kinds of tools, they had begun to search for the signs of these central giants in the more ordinary galaxies. Time after time, the evidence had shown that they were there even in the galaxies that were quiet and dim at the center. In some cases, the black hole was dormant and it was not actively consuming a great deal of material. But its gravitational pull was still measurable through the motion of the nearby stars and the gas clouds. It had soon become very difficult to be able to find a galaxy that did not have one of these at its center. The question had then shifted from, does our galaxy have a supermassive black hole, to why does every single galaxy seem to have one? The simplest answer would be that these black holes had formed alongside their host galaxies, and that they were perhaps a natural part of the process of galaxy formation. One idea is that in the very early universe, the clouds of gas had collapsed not into stars but directly into the massive black holes, which had then grown over billions of years by swallowing up the matter and by merging with the other black holes. Another possibility is that the very first stars, which were enormous ones that were far larger than any that exist today, had lived very short, violent lives, and that they had then collapsed into the massive seeds which had then, in turn, grown into the supermassive black holes. A key part of the puzzle is the strange link that is between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, which is the dense central region of the stars. Even in the galaxies that are very far apart in their size, this relationship is holding with a surprising level of precision. This is suggesting that the black holes and the galaxies are influencing each other's growth. If the black hole is feeding aggressively, then it can produce the winds and the jets that can push the gas away, which will slow down the process of star formation in the galaxy. If the galaxy is forming more of the stars, then more of the material might eventually fall toward the center, which will then feed the black hole. This two-way relationship is hinting at a very deep connection in their evolution, but no one yet fully understands how it works. The timeline of their formation is also very murky. Astronomers have found some quasars that are being powered by billion solar mass black holes at a time when the universe was less than 1 billion years old. That means that these monsters had formed incredibly quickly and far faster than our current models would suggest. To be able to grow that large in such a short amount of time, something very unusual must have happened. Perhaps there was an early phase of a rapid collapse of matter, or a series of frequent mergers between the smaller black holes. Sagittarius A star is a relatively small black hole. The black hole that is in the galaxy M87, for example, weighs in at several billion solar masses. And yet, despite the difference in their scale, Sagittarius A star is still fitting into the same cosmic pattern. Its presence is telling us that even a relatively modest galaxy like our own is still carrying this massive object at its very core. Some researchers have wondered whether it is even possible to have a galaxy without a supermassive black hole at its center. There are a few candidates for this. These are the small, faint galaxies where no central black hole has yet been detected. But the limits of our current technology mean that we might simply be missing them. It could be that these galaxies do have black holes, but that they are so small or so inactive that we are not yet able to see their effects. The deeper that we look, the more it seems that these central giants are fundamental to the life story of the galaxies. They may be acting as a kind of regulator, and they may be controlling the flow of the gas, the rate of the star formation, and even the very shape of their host galaxies. In some ways, they might be thought of as the engines that are driving the large-scale structure of the entire universe. In others, they are more like the silent governors, and they are influencing the events without always revealing themselves. The fact that we do not know exactly how they had first appeared is meaning that the story of the formation of the galaxies and the black holes is still incomplete. Were they born together side by side in the first cosmic dawn, or did the black holes come later, and were they carved out of the very first generation of the stars? The evidence is pointing in several different directions at once. By observing Sagittarius A star in a great deal of detail, we are able to test our theories about the growth of the black holes, the evolution of the galaxies, and the strange balance that seems to exist between a galaxy's stars and its own hidden heart. Every single insight that we are gaining here might be helping to explain the same kinds of structures in the far more distant galaxies, where the light has had to travel for billions of years to be able to reach us. Even with decades of study, the supermassive puzzle is still far from being solved. We now know the scale of the mystery, and that in itself is a kind of progress. But each new discovery about these cosmic giants is raising new questions about where they had come from and why the universe seems to be insisting on placing one of them in almost every single galaxy that it makes. If Sagittarius A star were to replace the Sun in our own solar system, its event horizon would completely swallow up Mercury, Venus, the Earth, and Mars, and we would not even have the time to notice before everything went dark. But in the realm of the universe's largest of the black holes, Sagittarius A star is not the king of the mountain. It is not even close. Take the black hole that is at the center of the galaxy M87. which is the same one that was famously imaged by the Event Horizon Telescope in 2019. This black hole is about 6.5 billion solar masses, which is over 1,600 times the mass of Sagittarius A star. It is big enough to be able to fit our entire solar system, including the Oort cloud, well within its own event horizon. Despite its enormity, the black hole of M87 is not even in the running for the largest that has ever been found. This is showing just how wild the size spectrum of these objects can be. Then there is Holm 15 amperes times, which is a central black hole that is in a galaxy cluster that is more than 700 million light-years away. This one has been estimated to weigh in at around 20 billion solar masses. It is sitting in the middle of a galaxy that is itself the largest that has ever been found, and it has a sprawling halo of stars. If Sagittarius A star were to somehow be swapped with Holm 15 amperes times the gravitational changes, would completely reshape the entire Milky Way. The orbits of the stars would shift dramatically, and the central bulge would become much denser and brighter from the intense gravitational pull. And then there is TON 618. This monster is one of the largest known black holes in the entire universe, and it is making Sagittarius A star look like a pebble that is sitting beside a skyscraper. The estimates are placing the mass of TON 618 at around 40 billion times that of our own Sunday. To be able to put that into perspective, you could line up over 10,000 different black holes that were the size of Sagittarius A star before you would be able to match its mass. The event horizon of TON 618 is so vast that the light would take about a week to be able to travel across it, compared to about 24 seconds for Sagittarius A star. The sheer scale of it is beyond our everyday comprehension. What is interesting is that even though these black holes are so much bigger, they may not be dramatically more dangerous in their own immediate environments. The pull of a black hole only becomes overwhelming when you are very close to it. Outside of that zone, its gravitational influence is just like that of any other object of the same mass. In other words, if our own sun were to be magically replaced by a black hole of an equal mass, the orbit of the Earth would remain completely unchanged. It would just be very, very dark and cold. The same is true on the scale of the galaxies. A bigger black hole does not mean that it is gobbling up the stars by the millions each and every day. It just has the potential to, if something were to stray too close. The difference is in how these black holes are growing and how active they are becoming. Sagittarius A star is a relatively quiet black hole. It is feeding on small amounts of gas and dust, and it is producing some weak flares of X-rays and radio waves now and then. In contrast, something like TON 618 is an active quasar, which means that it is devouring matter at a tremendous rate. As the material is falling toward it, it is forming a blindingly bright accretion disk, which is outshining the entire galaxies. This intense feeding frenzy is not only powering its brightness, but it is also allowing it to grow even larger over the cosmic time. Astronomers are thinking that Sagittarius A star may have once been much more active in the distant past. The evidence is suggesting that millions of years ago it could have flared up brightly enough to have sent some powerful radiation sweeping across the entire Milky Way. Some of the remnants of that activity might still be visible today, such as the mysterious Fermi bubbles, which are some enormous lobes of gamma-ray emission that are extending both above and below the galactic plane. If this is true, then Sagittarius A star might have been more like a small-scale quasar in its youth before it had settled into its current quiet phase. When they are comparing these cosmic giants, the scientists are also looking at how quickly they are spinning. The spin of a black hole can influence how it is pulling in the matter, how it is shaping the jets of the particles, and how its surrounding space is being warped. The spin of Sagittarius A star is still being measured with a great deal of care, but some of the larger black holes, like the one in M87, are believed to be spinning close to the maximum possible rate that is allowed by the laws of physics. This rapid spin can act like a kind of cosmic blender, and it can be whipping up the surrounding material and launching it out into space at near the speed of light. The spin of TON 618 is less certain, but given its sheer size and its level of activity, it is likely to have a very powerful reservoir of rotational energy. Sagittarius A star could have started out as a much smaller black hole that had then steadily grown by eating up the gas, the dust, and some unlucky stars. But TON 618 and Holm 15 amperes times must have had a head start. Some are suspecting that they had been formed from the collapse of the enormous gas clouds. Others are thinking that they had grown through multiple different mergers with the other black holes during the galaxy collisions. Sagittarius A star has probably gained some of its mass in this way as well. The Milky Way has had a history of merging with the smaller galaxies, and each one of them could have potentially brought its own central black hole with it. Over billions of years, these central objects could have sunk toward the center and then merged with Sagittarius A star, which would have added to its mass. While it is unlikely that our own galaxy will ever host a black hole that is as large as TON 618, the future mergers, including the eventual collision with the Andromeda galaxy, will give Sagittarius A star a significant growth spurt. In a few billion years, our own central black hole could become several times larger than it is today. These comparisons are also reminding us of the sheer range of the black hole environments that are in the universe. Sagittarius A star is in a fairly calm spiral galaxy, and it is surrounded by a mix of the old stars, the new stars, and some moderate amounts of gas. TON 618 is sitting in a far more active setting, and its quasar activity is lighting up the entire cosmos. The black hole of M87 is lying in a giant elliptical galaxy at the very heart of a dense cluster where the galaxies are frequently interacting and colliding. The size of a black hole is only a part of its story. The neighborhood that it is living in is playing an enormous role in shaping its behavior. The surprisingly quiet nature of our own giant black hole is because the black holes, by their very nature, do not slow down with age. If matter is falling toward them, then they will devour it. The difference is coming down to the amount of fuel that is available at the present moment. Sagittarius A star is surrounded by a relatively small amount of gas and dust compared to the central black holes of the more active galaxies. The material that does drift near to it is tending to be scattered or heated in such a way that much of it never makes it all the way to the event horizon. Instead, it is orbiting for a while. It is losing some of its energy, and then it is being pushed back out into space by the winds and the turbulence. Only a small trickle of the matter is actually reaching the point of no return. Because the feeding rate is so low, Sagittarius A star is very faint, at least in the terms of the black holes. Its emissions in the radio, infrared, and X-ray wavelengths are minimal compared to its more voracious cousins. The quasars can be thousands of times brighter. If our own black hole were to suddenly start consuming matter at the rate of an active quasar, then the night sky would never be the same. A brilliant source would appear at the center of the Milky Way, and it would be visible even in the daylight, and it would be outshining most of the stars. The idea is both fascinating and a little bit unsettling, as it would completely change the appearance of our own galaxy. This subdued state is one of the reasons why it was so difficult to find in the first place. If Sagittarius A star had been as active as the black holes in the quasars, then we might have been able to detect its presence much earlier. The first X-ray and radio detections of the galactic center were faint enough that the scientists had needed years of patient observation to be sure of what it was that they were seeing. Even at a distance of 26,000 light-years away, an actively feeding black hole would be an overwhelming beacon. The calm behavior of Sagittarius A star is telling the astronomers some things about its surroundings. It is suggesting that the central region of our own galaxy has been going through a relatively peaceful phase for millions of years. Other galaxies are showing the evidence of the violent outbursts from their own central black holes. There are the vast jets that are stretching for thousands of light years, the bubbles of the radio emission that are expanding out into the intergalactic space, and the shock waves that are heating up the surrounding gas. Our own galaxy is only showing some subtle hints of its past activity, like the Fermi bubbles. If so, then our own black hole is simply between its meals right now, and it is biding its time. Some of the scientists are believing that the quietness might just be a temporary state. There are the clouds of gas and the streams of the stars in the central region, and the orbital mechanics is ensuring that from time to time something will wander too close. When that is happening, a sudden flare of activity could occur. In fact, the astronomers have observed some brief outbursts from Sagittarius A star in the recent decades. There have been some sudden increases in the X-ray and the infrared brightness, and they have been lasting for only a few hours before they have been fading again. These could be being caused by small amounts of material that are falling in, which is producing a momentary flicker before the calm is returning. It is as if the giant is occasionally stirring in its sleep. Many of the most active of the quasars are hosting the black holes that are billions of times more massive than our own Sunday. Their sheer size is allowing them to be able to pull in much larger quantities of matter and to be able to radiate far more energy. That size difference may be partly explaining the level of their activity, since a smaller gravitational influence over the surroundings of Sagittarius A star might be limiting the amount of material that it is able to capture. Still, the size is not the only factor. There are some known black holes that have masses that are similar to or even smaller than Sagittarius A star, and that are far more active. This is reinforcing the idea that the main difference is the environment. If the central region of the Milky Way had a denser supply of gas and dust, then the story might be very different. In that alternate reality, Sagittarius A star could be blazing like the core of an active galaxy, and it could be influencing the star formation across the entire Milky Way and reshaping the very structure of our own home. When the astronomers are pointing their telescopes towards Sagittarius A star, they are able to see some details in the surrounding stars and the gas that would be hidden if the black hole were more active. This has allowed for some incredibly precise tracking of the stars that are in its vicinity. The calm environment is also meaning that the subtle changes in the brightness can be studied in a great deal of detail, which is giving us some insight into how the black holes are feeding even at very low rates. Even in this subdued state, Sagittarius A star is still emitting some radio waves. It is also producing some occasional X-ray and infrared flares, which, while they are faint compared to the quasars, are still significant for understanding its behavior. These flares are providing some brief glimpses of the processes that are occurring near the event horizon, and they are showing how the magnetic fields, the turbulence, and the hot plasma are interacting in these extreme conditions. There is a certain kind of mystery in watching something that is so massive, so fundamentally extreme in its nature, and yet so restrained. It feels almost unnatural, like a cosmic predator that is choosing not to hunt. Perhaps this is just a lull in its long and storied history. The galaxies are living for billions of years, and over such vast timescales, the feeding habits of their central black holes can shift very dramatically. A million years from now, Sagittarius A star may still be quiet, but perhaps in 25 million years, it will be in the middle of a feeding event, and it will be changing the appearance and the behavior of our own galaxy. The quietness is also having a benefit for the existence of life in our own galaxy. If Sagittarius A star were to be highly active, then the intense radiation from its core could potentially be affecting the planets that are even thousands of light years away. In the extreme cases, such radiation could be stripping away the atmospheres or altering the chemistry of the planetary surfaces. While the Earth is far enough away from the galactic center that such effects would be reduced, the overall habitability of the galaxy might be being influenced by whether the central black hole is active or not. In that sense, the current calm might be a small factor in why life has been able to develop and thrive here. The future of Sagittarius A star is depending largely on whether it is able to find any new food. Our own galaxy is not empty, but the material that is near the immediate surroundings of the black hole is relatively sparse. Most of the stars that are in the central region are in some stable orbits that are keeping them from falling in. The gas clouds are passing by, but they are not always close enough to be able to be caught. However, the galactic dynamics are very unpredictable over the long timescales. A close pass from a dense gas cloud or the disruption of a star could deliver a sudden meal. In fact, in the recent years, the astronomers had tracked a large gas cloud that was known as G2 as it was moving towards Sagittarius A star. Many had expected a dramatic flare-up when it had gotten close, but surprisingly the event was very mild. G2 had been stretched and distorted, but much of it had survived the encounter. This had shown that not every single close approach is resulting in a feast for the black hole. Still, the possibility is remaining that a larger or a denser cloud could one day be triggering a feeding frenzy. If enough material is falling in, then Sagittarius A star could become hundreds or even thousands of times brighter than it is now. The radiation would not be reaching the Earth in a dangerous form, but it would be changing the appearance of the night sky. The observers would be seeing the galactic center glowing far more intensely, and it would possibly even be visible to the naked eye under the dark conditions. Another path to a more active future could be coming from the galactic mergers. At some point, the Milky Way is expected to be colliding with the Andromeda Galaxy. When this is happening, billions of years from now, the stars themselves will be mostly passing by each other without any direct impact, but the gas and the dust that are within both of the galaxies will be stirred up and they will be funneled toward the centers. This could be delivering a massive influx of fuel to Sagittarius A star, which could be causing it to flare into a true quasar phase. In such a state, it would be unleashing the jets and the winds that could be reshaping the parts of the galaxy, and it would be blowing the gas away and potentially be halting the star formation in the surrounding regions. Looking at the other galaxies is giving us a hint of what such a transformation could be like. In the distant universe, the astronomers are seeing the supermassive black holes that are going through the cycles of activity. Some of them are in the middle of an intense quasar stage, while others are appearing to be dormant. This is suggesting that the black holes can have multiple different active periods over the course of their lifetimes. The timescales that are involved are so vast that human history is only a blink in the life of this object. It is possible that in 1,000,000 years or in 10 million, Sagittarius A star will still be quiet, but perhaps in 25 million years it will be in the middle of a feeding event, and it will be changing the appearance and the behavior of our own galaxy. There is even the possibility that it could be consuming an unusually large object like a star cluster or a passing intermediate mass black hole, which could be releasing the energy on a scale that is far beyond what we are seeing now. In the cosmic terms, the black holes are very patient. They do not need to be feeding constantly, and they can go through some long stretches without any dramatic events. But when the right conditions are arising, they can be shifting into a mode of intense activity almost instantly. The instruments like the Event Horizon Telescope, the space-based X-ray observatories, and the infrared telescopes are all helping to be monitoring the behavior of the black hole. The small fluctuations in the brightness can be giving us some clues about the material that is moving inward. Even though a major outburst could be far in the future, the process that is leading up to it might be being detectable years or centuries in advance. There is also a growing interest in looking for the historical traces of its activity in some other ways. Studying the orbits and the composition of the stars that are near the galactic center might be revealing the disturbances from the past energetic events. Mapping the gas structures in the central regions can also be showing the patterns that have been shaped by the older outflows. These are like the rings in a tree trunk, and they are the records of what the black hole has done before. If Sagittarius A star does enter another active phase, then it would be a rare chance to be able to study a supermassive black hole's transformation in real time. Most of the quasars that we are seeing are so far away that their light is coming from billions of years ago. To be able to witness such a thing in our own galaxy would be giving the scientists an unmatched opportunity to be able to understand the mechanics of the feeding and the feedback of the black holes. It would also be reminding us that the Milky Way, though it is feeling very stable, is still a dynamic and an evolving system. In the hearts of many of the galaxies, the presence of a glowing, furious ring of matter around a black hole is almost a given. These accretion disks are some massive swirling structures of gas, dust, and sometimes even the stars that have been caught in a slow, spiraling death toward the event horizon. As they are falling inward, the friction and the compression are heating the material to some incredible temperatures, and they are causing them to be radiating with the brightness of the entire galaxies. This is why the distant quasars can be outshining everything that is around them, and they are visible from billions of light years away. But when the astronomers had looked towards Sagittarius A star, they had not seen the blazing, unmistakable signature of such a disk. Instead, they had found something that was faint. It was so faint that for decades it had been uncertain whether it had existed at all. At first, this absence had puzzled the scientists. After all, the central black hole of our own galaxy was surrounded by the countless stars, the clouds of gas and the dust lanes that were twisting like the dark rivers through the galactic core. There had seemed to be plenty of raw material for the black hole to be consuming. The answer, as it is turning out, is lying not only in the black hole itself, but in the delicate balance of its environment. One of the earliest of the hints had come from the radio and the X-ray observations, which had revealed that while there was indeed some material that was moving toward the black hole, most of it had never made it all the way in. Instead, much of the gas had seemed to be slowing down, heating up, and then being blown outward before it was crossing the event horizon. This had led the researchers to be considering that Sagittarius A star might be being surrounded by what is called a radiatively inefficient accretion flow. In the simpler terms, this is meaning that the material that is falling toward the black hole is not radiating a great deal of light because it is not dense or compact enough, and much of it is escaping before the final plunge. Imagine that you are trying to build a bonfire, but instead of tightly stacking the logs together, you are scattering them loosely in a wide circle. The heat would still be there, but it would be escaping without creating the bright, intense flame that you would be expecting. This is similar to what is happening around Sagittarius A star. The gas that is spiraling in is too spread out and too unstable to be able to form a tightly packed, brilliant disk. Instead, much of it is swirling in loosely, and it is eventually being thrown back out into space by the powerful magnetic fields and the turbulent flows. There is also the question of the supply. For an accretion disk to be blazing with the brightness that is seen in the active black holes, it is needing a constant and a massive feed of matter. In the galaxies that are hosting the quasars, this feed is often coming from the intense bursts of star formation that are near the core, which are driving the vast amounts of gas toward the center. The Milky Way, however, is relatively calm at this stage in its life. While there are the stars that are orbiting very close to Sagittarius A star, and some of them are even swinging within a hair's breadth, on a cosmic scale there is no massive influx of gas. In fact, some of the studies are suggesting that Sagittarius A star might be in a long fasting period where it is consuming only a trickle of matter compared to its past. The evidence from certain X-ray echoes that are bouncing off of the nearby gas clouds is hinting that just a few hundred years ago, our own black hole may have been much brighter. If this is true, then that is meaning that the ghostly disk that we are seeing today might be a remnant that is slowly dissipating in the absence of a fresh supply of material. The search for the missing disk had taken on a new urgency when the Event Horizon Telescope had turned its gaze towards Sagittarius A star. The EHT, which is a global network of the radio telescopes that are working together to be able to act as a planet-sized observatory, was able to be resolving the faint halo of emission that was around the black hole. What they had seen was not a flat, bright disk, like the one that had been imaged around the black hole in M87, but a more irregular and a patchy structure. This had reinforced the idea that the accretion flow of Sagittarius A star is thin, hot, and chaotic, and that it is producing far less radiation than one might be expecting. But this is not meaning that the disk is unimportant. Even a faint accretion flow can be providing some clues about the behavior of the matter in the extreme gravity. The weak emission that we are detecting is giving the scientists a way to be able to measure the temperature, the density, and the motion of the gas. These measurements are suggesting that the plasma that is near Sagittarius A star is incredibly hot, and it is at tens of millions of degrees, yet it is still too tenuous to be able to produce the blinding light of a more active system. Another piece of the puzzle is coming from the orbits of the stars, which are passing close enough to Sagittarius A star to be potentially shedding some material into its gravitational pull. Yet the accretion disk is remaining faint. This has led to some speculation that the black hole may be being very selective about what it is consuming. The magnetic fields and the turbulent flows in the surrounding plasma could be acting like a kind of cosmic shield, and they could be deflecting much of the infalling gas before it is able to reach the inner disk. Still, the mystery is remaining. Was the ghostly disk always like this, or is it the result of a recent drop in the feeding? Will it be flaring to life again if a large cloud of gas or a star is drifting too close? In 2014, G2 had passed with little more than a murmur. This may have been because G2 was a star that was cloaked in dust rather than a free-floating gas cloud, which would be explaining why so little material had ended up in the disk. What is certain is that the missing accretion disk is not truly missing. It is simply faint, fragmented, and underfed. For now, we are living alongside a sleeping giant whose hunger is subdued. Every so often, the calm, dim glow that is around Sagittarius A star is broken by a sudden burst of light that seems to be coming from nowhere. These flashes, or flares as the astronomers are calling them, are appearing without any warning. One moment, the region that is near the black hole is quiet and subdued. The next, it is as if someone has turned up the cosmic brightness knob for a brief moment before they are letting it fade again. These flares can be very dramatic. Sometimes the brightness can be increasing dozens of times above its usual level, and it is only to be returning to normal within a couple of hours. They are not happening on a fixed schedule. They are not being tied to anything that is obvious that we can see in advance. And because Sagittarius A star is hidden behind the thick clouds of gas and dust, the suddenness of these events is making them all the more intriguing. When a flare is happening, the scientists are dropping whatever else it is that they are doing, and they are pointing every available telescope at it, and they are trying to gather every single scrap of information before it is fading. The first time that the astronomers had noticed these flares, they had been surprised by both their intensity and their speed. The timing had suggested that the flares were coming from very close to the event horizon. The rapid rise and fall in the brightness had hinted that the source was very compact, and it was no larger than the distance that the light could be traveling in a few minutes. This was a very strong clue that something that was near the heart of the immediate surroundings of the black hole was responsible. But what exactly was it? One of the possible explanations is that these flares are being caused by the clumps of gas that are falling inward. In the normal conditions, the matter that is around Sagittarius A star is too thin and too sparse to be able to produce a great deal of light. But occasionally a denser pocket of material, which might be from a nearby star that is shedding its outer layers, or a cloud of dust that is drifting too close, could be finding itself being caught in the pull of the black hole. As it is spiraling inward, the gas is heating up to millions of degrees, and it is releasing a burst of energy before it is vanishing into the black hole. This would be creating a sudden flare. Another possibility is involving the magnetic fields. The black holes can be twisting and tangling the magnetic field lines in their surroundings, and they can be storing enormous amounts of energy. If these magnetic fields are suddenly reconnecting, which is a process that is similar to what is happening in the solar flares on our own sun, then they could be unleashing a rapid burst of radiation. In this view, the flare is not just a side effect of the matter that is falling in, but a direct release of the pent-up magnetic energy. This could be explaining why some of the flares are appearing without any sign of new material being swallowed. A third idea is that the flares are being caused by the stars or the smaller black holes that are passing dangerously close to Sagittarius A star. In such encounters, the tidal forces could be ripping apart the chunks of material, and they could be sending them spiraling into the black hole and producing an intense flash. While this is less likely to be happening frequently, it cannot be ruled out. After all, the galactic center is a very crowded place. The astronomers cannot just schedule an observation and be expecting a flare to appear. It is a waiting game. The teams are sometimes monitoring Sagittarius A star for weeks at a time, and they are hoping to be able to catch even one single brightening event. And when they are doing so, they must be reacting very quickly, and they must be coordinating with the telescopes that are on the ground and in space to be able to record the flare across as many of the wavelengths of light as is possible, from the radio waves to the X-rays. The goal is to be able to piece together a complete picture of what is happening during these brief episodes. Interestingly, the flares are tending to be occurring more often in the X-ray and the infrared light than in the visible light. This is fitting in with the idea that they are being caused by the very hot material that is close to the black hole, since such high-energy environments are naturally emitting more in these parts of the spectrum. But even with this knowledge, there is no simple pattern. Some of the flares are stronger in the X-rays and others are stronger in the infrared. Some of them are lasting for only a few minutes while others are lingering for hours. The variety is suggesting that more than one single process might be at work. A particularly famous flare had happened in 2019 when Sagittarius A star had become brighter than it had ever been recorded before, and it was more than twice its previous maximum. The intensity had shocked the scientists, and for a brief moment they had wondered if something major had happened, like a star being torn apart. But the follow-up observations had suggested that it was likely a massive clump of gas that had been falling in, and that it was perhaps related to G2, which had been drifting near the black hole for years by this point. This event had shown just how dramatic Sagittarius A star can be when it is deciding to stir from its usual slumber. If such bursts can be happening today in its relatively quiet state, then what might they have looked like in the past when the black hole was more active? The evidence from the X-ray echoes that are in the nearby clouds is suggesting that hundreds of years ago, Sagittarius A star may have been hundreds of thousands of times more luminous than it is now. In that light, today's flares might be the small-scale reminders of a much wilder, more energetic past. For now, the bursts are brief and isolated, but if the surroundings of the black hole are changing, then it could be feeding much more vigorously. The occasional flare might be the cosmic equivalent of a stomach growl before a real feast is beginning. The scientists are hoping that by studying more of the flares in a great deal of detail, they can be narrowing down the causes and be understanding the physics that is at play. The coming years should be bringing some major improvements in this field. The instruments like the EHT are now being used to be able to watch Sagittarius A star directly. Combined with the space-based X-ray and the infrared telescopes, these observations could finally be allowing the astronomers to be able to see a flare as it is forming, to be able to track its evolution in real time and to be able to match it to the specific physical processes. Close to the edge of Sagittarius A star, the rules of the universe are starting to feel less like the constants and more like the shifting patterns. Here, the gravity is not the only dominant force. The invisible but incredibly powerful magnetic fields are twisting and writhing like the living things. They are threading through the surrounding space, and they are wrapping around the arcs of the plasma, and they are guiding the flow of the charged particles, and sometimes perhaps they are choking it off entirely. For a long time, the astronomers had assumed that the magnetism that was near a black hole was just a byproduct, and it was a background feature of the swirling gas. But now it is becoming clear that these tangled fields might be at the very heart of the strange behavior of the black hole. The idea of the magnetic fields that are near a black hole might be sounding almost contradictory. After all, a black hole is swallowing everything that is coming too close. How could anything be surviving there, let alone a structure that is as delicate as a magnetic field? The key is that the black hole itself is not generating them in the same way that the molten core of the Earth is producing our own magnetic field. Instead, the fields are coming from the plasma that is surrounding the black hole. As this gas is moving, it is dragging its own magnetic field lines with it, and it is stretching and twisting them into the complex knots. The magnetic fields of Sagittarius A star are not the neat, stable loops like the ones that are around our own planet. They are chaotic, and they are constantly shifting as the gas that is around them is flowing, colliding, and heating up. The polarized light data from the EHT has given the astronomers the first real look at these magnetic structures, and it is revealing the spiraling patterns in the faint glow that is around the black hole. The patterns are telling us that the fields are strong enough to be able to shape the motion of the matter and not just to be passively drifting through it. In a way, the magnetism is competing with the gravity here. The gravity is wanting to be pulling everything inward, and it is dragging it toward the event horizon. The magnetic fields can be pushing back, especially when they are becoming tightly wound. They can be acting like the barriers, and they can be holding the material in place or be redirecting it along the certain paths. This could be a part of the reason why Sagittarius A star is so quiet. If the magnetic fields are being organized in a certain way, then they might be preventing the gas from plunging in all at once. Instead, the material is trickling in very slowly, and it is producing only the weak emission. But these same magnetic fields can also be storing the enormous amounts of energy. When they are snapping or realigning, then they can be unleashing the bursts of radiation. A sudden reconnection event that is near the event horizon could be accelerating the particles to the extreme speeds, and it could be causing them to be emitting the X-rays and the infrared light in the short, sharp flashes. The flare is fading as the energy is dissipating, and it is leaving the black hole dim again until the next event. There is also a mystery about how these magnetic fields are being arranged in the 3 dimensions. Some of the models are suggesting that they could be forming the large-scale loops that are extending far from the black hole, and they could be threading through the surrounding region that is known as the accretion flow. Others are proposing a much more tangled mess where the lines are constantly breaking and reforming. The observations so far are hinting at some degree of order that is close to the black hole, but some chaos that is farther out. This could be meaning that the environment of Sagittarius A star is in a very delicate balance, and that it is stable enough to be avoiding the constant eruptions, but that it is unstable enough to be producing the occasional bursts of activity. In the other systems, the strong fields can be launching the powerful jets, which are the beams of the plasma that are shooting out at near the speed of light. Sagittarius A star is not having the obvious large-scale jets, but there are the hints of the smaller, weaker outflows. If the magnetism is being involved, then these outflows might be acting as a kind of pressure valve, and they could be releasing the energy and the gas that would otherwise be feeding the black hole more directly. This could be another reason why it is staying so faint most of the time. Near the event horizon, the conditions are so extreme that the usual rules for how the plasma is behaving are beginning to break down. The magnetic fields can be influencing the particles in the ways that we cannot be fully modeling yet, especially when the relativistic effects are being involved. The charged particles that are spiraling along the field lines at near the speed of light can be producing the polarized radiation. And by studying that polarization, the astronomers can be decoding the shape and the strength of the field. The patterns in this light are some of the few direct clues that we are having about what is happening in a region that we can never be visiting. The magnetism that is near Sagittarius A star is a part of a larger story about the interplay of the forces in one of the universe's most extreme environments. The gravity may be dominating the structure, but the magnetism is adding a layer of complexity that is changing how the black hole is feeding, flaring, and interacting. It is an invisible architecture that is shaping a cosmic environment just beyond the point of no return. The more that we are understanding about these twisting fields, the closer we are getting to understanding the hidden engines that are powering the black holes across the entire universe. The Schwarzschild radius is one of the simplest ways to be able to describe a black hole. It is the size of the event horizon. If you are crossing this line, then you are gone from the visible universe forever. The term is coming from the German physicist Karl Schwarzschild, who in 1916 was the first to be finding a mathematical solution to the new theory of general relativity of Einstein that was describing such an object. His equations were telling us that if you are compressing enough mass into a small enough space, then the pull of the gravity is becoming absolute at a certain radius. That radius is depending only on the mass of the object. And for the black holes, it is all that is being left to be defining their size. For Sagittarius A star, the mass is about 8.54 times 10 to the power of 36 kilograms. When you are plugging that into the Schwarzschild formula, then you are getting a radius of roughly 12 million kilometers, or about 7.4 million miles. That is sounding huge, and in the human terms it is. But in the cosmic terms, it is surprisingly small. It is just over 17 times the diameter of our own Sunday. All of it is packed into an invisible sphere that is at the very heart of the Milky Way. Everything that is inside of that sphere is being cut off from the rest of the universe. The black hole itself is not a physical ball. The event horizon is not a solid surface that you could be touching. It is simply the threshold where the space and the time are bending so steeply inward that no outward path is existing. From far away, the Schwarzschild radius is a purely mathematical line. You could be orbiting near it, and you could be circling around it, and you could even be hovering just outside of it if you were having some impossible way to be counteracting the gravity. But if you are getting closer, then the landscape is changing. The space itself is falling inward, and it is being pulled faster and faster as it is approaching the event horizon. The closer that you are, the more extreme the time dilation is becoming. From your own perspective, everything would be seeming to be normal. From the outside, you would be appearing to be slowing down, and your light would be shifting to the red, and it would be fading, and it would eventually be disappearing entirely before you are ever seeming to be crossing the line. The Schwarzschild radius is marking the point where the inward pull is becoming infinite from the perspective of the outside universe. The Schwarzschild radius of Sagittarius A star has been the focus of the intense study in the recent years, especially with the EHT. The image of Sagittarius A star from the EHT is showing a glowing ring of the radio light that is around a dark center. That dark center was not the black hole itself, but its shadow, which was a slightly larger silhouette that was being caused by the light that was being bent and swallowed near the event horizon. The actual Schwarzschild radius is lying just inside of the edge of that shadow. In this sense, we have now seen the boundary, even if it is not in a direct visual photograph. Because it is so far away, the whole thing is appearing to be smaller in the sky than a donut on the moon would be looking to someone who was standing on the Earth. That is why imaging it had taken the years of the coordination, the enormous computing power, and the precision of the atomic clocks. Beyond the Schwarzschild radius is lying the region that we cannot be observing directly. According to the general relativity, once you are passing the event horizon, then you are inevitably being drawn toward the singularity that is at the center. The singularity is a point of the infinite density where the known laws of physics are breaking down. We are not knowing what is really happening there. Some of the theories are suggesting that it might be a tiny, infinitely curved region of the space-time. Others are proposing that the quantum effects could be smearing it out, or be replacing it entirely with something that is new, perhaps a Planck star or a bridge to another universe. But as far as our instruments are being concerned, it is forever being hidden. The Schwarzschild radius is not just a limit for the light. It is a limit for the cause and the effect. No signal from the inside can ever be influencing the outside. That is meaning that the inner workings of a black hole are being cut off from the rest of the cosmos in a very fundamental way. This is why so much of the science of the black holes has to be being done indirectly. We are measuring the orbits of the nearby stars, and we are watching how the hot gas is behaving, or we are detecting the flickers of the light that are being caused by the magnetic or the gravitational turbulence just outside of the event horizon. Sagittarius A star is not unique in having a Schwarzschild radius of this size. Any object of 4 million solar masses would be having the same value. What is making it unique is its position in our own galaxy, and the fact that we can be studying it in a great deal of detail compared to the others. The black holes with the billions of the solar masses are having much larger event horizons, and they are sometimes bigger than our entire solar system. In the contrast, a stellar mass black hole might be having a Schwarzschild radius of only a few kilometers. This is why the scientists are often describing the black holes in the terms of their mass rather than their physical size. It is the mass that is determining the radius in the first place. Once you are knowing the mass of a black hole, then you are knowing its Schwarzschild radius. You are also knowing something about the speed that is being needed to be escaping from just outside of it. The escape velocity is being equal to the speed of light. That is the defining trait. For any other object, the planets, the stars, and even the neutron stars, the escape velocity is being lower, which is meaning that the light can still be getting out. But at the Schwarzschild radius, the pull is being too strong for even the photons. Near the Schwarzschild radius of Sagittarius A star, the conditions are violent even in its current quiet state. The magnetic fields are twisting and snapping, the charged particles are spiraling at near the speed of light, and the space-time itself is being dragged around by the spinning black hole. Even though Sagittarius A star is relatively calm now, the zone that is just outside of the horizon is still an extreme laboratory for the physics. It is here that the matter in the accretion flow is heating to the millions of the degrees and is emitting the radio waves that the EHT had detected. It is here that the flares of the X-rays and the infrared light are sometimes bursting out when the clumps of the gas are plunging inward. In the mid-20th century, the center of the Milky Way was still mostly a mystery. Throughout the 1980s, radio astronomy remained the primary tool for studying this strange source. The observations with the VLA in New Mexico sharpened the view, showing that Sagittarius A star was not only compact but also variable. Its radio output would rise and fall over time. The next leap forward came from pushing interferometry to a much greater scale. In the 1990s, scientists began linking radio dishes spread across the globe in a technique called Very Long Baseline Interferometry, or VLBI. This allowed them to create a virtual telescope the size of the Earth, dramatically improving the resolution. By combining the data from observatories that were thousands of kilometers apart, they could begin to measure the apparent size of Sagittarius A star, which was just tens of micro-arcseconds across. In the 1990s, infrared astronomy came into its own, thanks to new detectors and adaptive optics systems that could counteract the blurring effects of the Earth's atmosphere. Over years of careful measurement, two separate teams mapped how the stars moved in tight, fast orbits around the invisible point. NASA's Chandra X-ray Observatory, which was launched in 1999, revealed that Sagittarius A star occasionally emits bright flares in X-rays, showing that it was not entirely dormant. The Spitzer Space Telescope mapped the crowded star fields and the warm dust near the center with an unprecedented clarity. By moving above the Earth's atmosphere, these observatories were able to bypass the distortions and the absorbed wavelengths, which allowed the scientists to gather cleaner, more detailed data. In the 2000s, submillimeter astronomy became another major tool. This part of the spectrum, which is between the infrared and the radio, is especially good for studying the cold dust and the emission from the matter that is close to the black holes. The submillimeter array in Hawaii and later the Atacama Large Millimeter divided by Submillimeter Array, or ALMA in Chile, gave the researchers a sharper look at the surroundings of Sagittarius A star. These arrays, with their high-altitude locations and their wide baselines, could detect the fine details in the faint emissions that were coming from the galactic center. The ultimate imaging challenge, however, was to be able to see the shadow of the black hole itself, which was a feat that was only possible by pushing VLBI to the extreme. This is where the Event Horizon Telescope, or EHT, came in. Starting in the 2010s, the EHT linked together a network of radio observatories that were scattered across the globe, including ALMA, the South Pole, Telescope, and others in North America, Europe, and Asia. The observations were conducted at 1.3 millimeters, which is a wavelength that can pass through much of the galactic dust while offering an incredibly high resolution. In 2017, the EHT turned its full attention to Sagittarius A star. Processing the data took years because the appearance of the black hole changes very rapidly. The material that is whirling close to the event horizon is moving at near the speed of light, which is causing the brightness pattern to shift in just minutes. Combining the data from the multiple sites into a coherent picture required some complex algorithms and a careful averaging over time. Finally, in 2022, the EHT team released the first ever image of Sagittarius A star. It was a blurry but unmistakable ring of light that was surrounding a dark central shadow. It was exactly what the theory had predicted for a black hole of its mass. Each step in this process reflects both the technological progress and the persistence of the scientists who were involved. From the first crude radio detections to a direct image of the event horizon's silhouette, the journey spanned decades and required innovations in instrumentation, computing, and observation techniques. New instruments such as the James Webb Space Telescope are now probing the galactic center with an unmatched sensitivity in the infrared, while the upgrades to the EHT are promising even sharper images in the years ahead. The discovery of Sagittarius A star has been a gradual unveiling. Each generation of instruments has been peeling back another layer of the mystery. And with every improvement in our tools, we are seeing a living, changing part of the story of the Milky Way. Light does not simply travel in straight lines through an empty stage. Instead, the very fabric of space can bend it, twist it, and even focus it like a giant lens. This bending of light, which is known as gravitational lensing, is one of the most extraordinary tools that nature itself has provided to the astronomers. For the researchers who are studying Sagittarius A star, this natural phenomenon has, in certain cases, given us some sharper glimpses into the dark heart of our own galaxy. Imagine placing a heavy ball on a rubber sheet. The ball will sink in and it will create a depression. Now, if you were to roll a marble across the sheet, it would curve around the dip rather than moving in a straight path. In space, the massive objects like the stars or the black holes are playing the role of the heavy ball, and the light is the marble. The sheet is the invisible fabric of space-time. When the light from a distant object is passing near something that is massive, the gravity of that object is warping the space-time and is changing the path of the light. To us who are observing from afar, it can look as if the light has been bent or focused. When this is applied to Sagittarius, A star gravitational lensing is becoming more than just a clever trick of physics. The galactic center is packed with the stars, the clouds of gas, and the other dense objects. Sometimes these objects are passing between us and Sagittarius A star, and they are briefly bending the light in the ways that are allowing the astronomers to be able to gather more detail than they could otherwise. This can be especially valuable because our line of sight to the galactic center is normally being clouded by the dust. The lensing can be acting like a cosmic cleaning of the lens, and it can be allowing for more clarity in the moments when it is aligning just right. The effect can be occurring on different scales. In some cases, the individual stars that are orbiting very close to Sagittarius A star can be acting as the tiny lenses, and they can be magnifying the background objects. This microlensing can be helping the researchers to be able to detect the faint objects that would otherwise be invisible. In the other cases, the entire regions of the dense gas or the clusters of the stars can be creating a larger lensing effect, and they can be warping the light from the even more distant sources. By studying these distortions, the scientists can be reconstructing the paths of the light and be learning more about what is lying in the center of the Milky Way. Not only can the intervening objects be lensing the light from the galactic center, but Sagittarius A star itself, with its immense gravity, can be bending the light from the background stars. This bending can be causing the multiple images of the same star to be appearing, or it can be stretching the light of the stars into the arcs. By carefully measuring these distortions, the astronomers can be getting the extremely precise readings of the mass of the black hole and even the hints about the distribution of the matter that is near the event horizon. However, capturing these events is not an easy task. Gravitational lensing is requiring a near-perfect alignment between the observer, the lensing object, and the background source. These alignments are rare, and they are often short-lived, especially in the dynamic environment that is around the galactic center. The observatories have to be ready to be monitoring this region constantly, and they have to be watching for the subtle shifts in the brightness or the position that are signaling a lensing event. This is where the networks of the telescopes that are spread across the globe are becoming critical. They can be watching the same spot from the different locations, and they can be ensuring that nothing is being missed. The first hints of the gravitational lensing effects that were near Sagittarius A star were not immediately being recognized for what they were. The early radio astronomers had sometimes been noticing the odd brightening of the background sources, but the tools to be able to confirm the lensing were not yet being refined. As the technology had been improving, and as the theories of how the lensing is working had been becoming more widely accepted, these earlier data points had been gaining a new meaning. Now the researchers can not only be identifying the lensing events, but they can also be predicting them in some cases thanks to the detailed tracking of the movements of the stars. Even with our most advanced of the telescopes, the region that is just outside of the event horizon is tiny from our own perspective. The lensing is allowing us to be peeking into this zone with a boost in the resolution, and it is offering the insights into the shape of the accretion flow, the distribution of the magnetic fields, or the dynamics of the orbiting material. These details are essential for testing our models of the behavior of the black holes. Another subtle benefit of the gravitational lensing is that it can be acting as a natural amplifier for the faint bursts of radiation. Sometimes a lensing effect can be making a flare stand out more clearly against the background, and it can be allowing the researchers to be able to study its timing, its duration, and its intensity with a better accuracy. In some of the rare alignments, the light of the flares might even be taking two different paths around the black hole before it is reaching us, and it could be creating a delayed echo that can be measured. While the gravitational lensing is often being described in the terms of its visual impact, it is also playing a role in the other wavelengths. The radio waves, the infrared light, and even the high-energy X-rays can be being bent by the gravity in exactly the same way as the visible light is. This is meaning that the benefits of the lensing are applying to the full range of the observations that are being used to be studying Sagittarius A star. The radio arrays, the infrared observatories, and the X-ray satellites have all been recording the data that is hinting at or directly showing the lensing effects that are near the galactic center. If Sagittarius A star is ever becoming brighter and more violent, then the gravitational lensing could be magnifying the effects of its outbursts. This might be making the activity of the black hole visible to the observers who are much farther away, and it could potentially even be making it visible to the civilizations in the distant galaxies. In this way, the lensing is not just aiding our own study of the black hole, it could also be helping to be spreading its presence across the entire cosmos. While it is already proving to be useful, many of the researchers are believing that we have only scratched the surface of what it can be revealing. With the next generation of the instruments, and the observatories, including the instruments that are capable of the even finer resolution and the sensitivity the coming decades could be seeing, the gravitational lensing being used as a standard tool for probing the deepest secrets of the central black hole of our own galaxy. The light from the stars that are near Sagittarius A star has to be passing through the thick layers of the atmosphere of the Earth before it is reaching the detectors. This atmosphere, while it is essential for the life, is far from being friendly to the delicate astronomical measurements. The air currents are moving unpredictably. The pockets of the warmer and the cooler air are bending and twisting the incoming starlight in the different ways. This bending is changing constantly, and it is causing the stars to be appearing as though they are shimmering or wobbling, which is an effect that anyone can be seeing by looking up at the twinkling stars on a clear night. For the astronomers who are trying to be tracking the fine details of the stars that are orbiting very close to the black hole, that twinkling is not a charming thing. It is a serious problem. For a long time, this distortion had been meaning that even the most powerful of the ground-based telescopes could not be producing the perfectly sharp images of the galactic center. The solution had been coming from a breakthrough in the technology that is called the adaptive optics. Instead of simply trying to be designing the better lenses or the mirrors to be working around the problem, the adaptive optics is attacking the issue at its very source, which is the moving atmosphere. The basic idea is that if the atmosphere is bending the starlight, then a telescope could be using a flexible mirror that is bending in the opposite way, and it could be undoing the distortion in real time. To be able to figure out exactly how to be bending that mirror, the astronomers are first needing to be measuring the distortion. In the practice, they are doing this by aiming at a bright reference point in the sky. Sometimes this is a real star, but often the astronomers are creating an artificial one by shining a powerful laser into the upper atmosphere. The laser is exciting the sodium atoms that are about 90 kilometers above the Earth, and it is making them be glowing and be forming a bright point of light. By analyzing how the light of this artificial star is getting warped on its way down, the computers can be instantly calculating the changes that are being needed for the mirror. The surface of the mirror is shifting and flexing hundreds of times per second, and it is counteracting the effects of the atmosphere. When the adaptive optics had first begun to be being used for studying Sagittarius A star, it had been nothing short of a revolution. The stars that had once been looking like the fuzzy patches had suddenly been coming into the sharp focus. The true structure of the central star cluster had been emerging in an unprecedented detail. The astronomers could now be tracking the movement of the individual stars as they were swinging around the invisible mass that was at the center. The adaptive optics had also been allowing the researchers to be studying the light from these stars in a finer detail. The spectroscopic measurements, which are splitting the light into its component colors, had been becoming more precise. This had been opening the door to be learning about the speeds, the chemical compositions, and the interactions of the stars with the extreme environment that was near the black hole. The difference between the pre-adaptive optics and the post-adaptive optics data was like switching from a cloudy lens to the high-definition vision. But even with this technology, the galactic center is not an easy place to be observing. The dust clouds are still blocking much of the visible light, so the astronomers are often working in the infrared range. The adaptive optics is working in the infrared too. And that combination, the infrared sensitivity and the real-time atmospheric correction, has been the key to be unlocking many of the discoveries about Sagittarius A star. Without it, some of the most important of the measurements, such as the gravitational redshift of the light from S2 or the precise mapping of the stellar orbits, would have been impossible. The atmosphere of the Earth is constantly changing, with the turbulent patterns that are evolving over the milliseconds. The system's computers must be detecting, calculating, and correcting for these changes in the same time frame. The mirrors that are being used are highly specialized, and they are often made of the thin, flexible materials like the glass or even the metal, and they are coated with the reflective surfaces. The tiny actuators are pushing and pulling on the different points of the mirror to be creating just the right shape. The precision that is being involved is almost hard to be grasping. The movements are often smaller than the width of a human hair, yet they are having a profound impact on the clarity of the image. Over time, the technique has been being refined. The early systems could be correcting for the general distortions, but they had been struggling with the finest of the details. The modern systems that have been installed on some of the world's largest of the observatories can be accounting for the different layers of the atmosphere separately. This is important because not all of the turbulence is happening at the same height. The wind patterns in the lower atmosphere, the jet streams at the high altitude, and the localized heat that is rising from the ground are all playing the different roles in bending the light. The multi-conjugate adaptive optics, as it is being called, is using the several reference points and the multiple deformable mirrors to be addressing these layers independently. The result is a broader and a more uniform correction, which is especially useful for the wide-field imaging of the galactic center. For Sagittarius A star, this has been meaning that the astronomers can now be doing more than just tracking the stars. They can be looking for the subtle changes in the brightness, or the position that might be hinting at the unseen companions, the faint clouds of gas, or the motion of the hotspots that are near the event horizon of the black hole. The adaptive optics has even been being combined with the interferometry. This approach is pushing the resolution even further, and it is allowing the scientists to be peering into the regions that were once being thought to be completely unreachable from the ground. The success of the adaptive optics has not been going unnoticed. It is now being considered to be a standard tool for the cutting-edge astronomy, and the lessons that have been learned from studying Sagittarius A star have been influencing its development for the other purposes. The observations of the distant galaxies, the exoplanets, and even the asteroids have all been benefiting from this technology. But in the case of the black hole of the Milky Way, the impact has been especially profound. It has been turning what was once a turbulent and a shifting image into a clear, steady view, and it has been revealing a dynamic and a crowded region where the gravity is reigning supreme. And while the adaptive optics has been transforming our view from the Earth, it is working best when it is being paired with the other methods. The space telescopes, which are free from the atmospheric distortion, are still providing the unmatched stability, but they cannot be having the mirrors that are as large as some of the ground-based observatories. Combining the size and the power of these giant Earth-based telescopes with the atmospheric correction of the adaptive optics has been creating a balance. We can now be studying Sagittarius A star with a level of detail that would have been unthinkable just a few decades ago. In 2019, the world saw a picture of M87*. M87 times has a mass that is about 6.5 billion times that of our own Sun, which is making its event horizon huge in comparison. Its size was one of the reasons why the scientists had chosen to be targeting it before Sagittarius A star. A bigger black hole is producing a larger shadow against the surrounding light, which is making it easier to be imaging despite its incredible distance. The larger mass is also meaning that the matter that is orbiting near the event horizon is moving more slowly, so the changes in the brightness are happening over the hours or the days rather than the minutes, as with Sagittarius A star. This had been giving the astronomers more time to be gathering the data that they had been needing without the image becoming too blurred by the rapid changes. No single telescope on the Earth is big enough to be able to see the event horizon of a black hole. To be able to get the necessary resolution, the telescope would be needing to be about the size of our own planet. Since that is obviously not possible as a single instrument, the scientists had been linking the radio telescopes across the globe to be forming the EHT. By coordinating these facilities to be observing M87 times at the same time and precisely combining the data from each, the scientists could be effectively creating an Earth-sized telescope in the terms of the resolution. The precision that was being required for this was mind-boggling, and it was down to be syncing the atomic clocks that were so accurate that they would be losing less than a second over the millions of years. Each of the observatories had been collecting the vast amounts of data which could not simply be being sent over the internet because the volume was so large. Instead, the data had to be being physically stored on the special hard drives and being flown to a central location for the processing. The observation campaign for M87 times had taken place in April of 2017. For several nights, every single one of the participating telescopes had been pointing toward the galaxy, and they had been recording the high-frequency radio waves that were being emitted by the matter that was swirling near the event horizon. These observations had taken place at a wavelength of 1.3 millimeters. The weather had to be being perfect at every single site that was being involved, because the poor conditions at even one single telescope could be ruining the data. After the observing run, the real work had been beginning. The petabytes of the raw data had been being shipped to the powerful computing centers, where the teams of the scientists had been beginning the process of correlating and calibrating the signals from all of the telescopes. This step was essential because each of the telescopes had been recording the slightly different information, and the timestamps had to be being matched perfectly to be reconstructing the interference patterns. These patterns had then been being used to be generating an image, but even that had not been as straightforward as taking a photograph. There had been the gaps in the coverage of the virtual Earth-sized telescope, so the algorithms had to be filling in the missing details. To be avoiding the bias, the imaging process had been being split among the multiple independent teams, and each of them had been working without the knowledge of the results of the others. When the images had finally been being compared, they had been matching very closely. On April 10, 2019, the EHT team had been revealing the image to the entire world. A blurry orange donut against a black background, which was representing the light from the hot matter that was bending around the event horizon of M87*. It was a visual confirmation of the general relativity in one of the most extreme environments in the entire universe. The size and the shape of the shadow had been matching the predictions almost perfectly. The photo had instantly been becoming one of the most iconic images in all of science. It had been proving that the millimeter wavelength interferometry could be imaging the black holes, which was something that many had been thinking might be impossible. It had also been opening the door to be eventually imaging Sagittarius A star. While our own black hole is closer and is appearing to be larger in the sky than M87 times, it is also far more challenging to be photographing. The success of M87 times was a critical test run. It had been allowing the scientists to be refining their techniques, to be improving their algorithms, and to be gaining the confidence that was being needed to be attempting the more difficult target in our own galaxy. It had also been teaching them about the behavior of the black holes in general. The bright ring that had been seen in the image had been being caused by the synchrotron radiation from the electrons that were spiraling along the magnetic fields. The asymmetry in the brightness of the ring had been showing that the matter that was around the black hole was moving at near the speed of light, with one side being boosted in the brightness due to the relativistic effects. Since that first image, the EHT has been expanding, and it has been adding more of the telescopes to be increasing its resolution and its sensitivity. It has also been starting to be working at the multiple wavelengths to be probing the different aspects of the black holes. The lessons from M87 times are continuing to be influencing how the scientists are thinking about the physics of the black holes as a whole. The road to that first photo was a testament to the global cooperation in the science. The teams from the different countries with the different expertise and the languages had been working together toward a single goal to be seeing the unseeable. It is easy to be forgetting how much of this had been uncertain in the beginning. Before the EHT, no one had been knowing if the turbulent gas that was around a black hole would even be producing a clean enough shadow to be detecting. The fact that the image had been turning out so clear and so close to the theoretical predictions had been giving the researchers more confidence in the models that they had been using to be studying the cosmos. It had also been inspiring a new wave of the scientific projects that were being aimed at pushing the limits of the imaging technology even further. Already, there are the proposals for the next generation EHT arrays that would be including the telescopes in space, which would be providing the even longer baselines and the sharper resolution. One day, it might even be being possible to be making the time-lapse movies of the matter that is falling into a black hole, and they would be showing in real time the dance of the energy and the gravity at the very edge of physics. The image of M87 times had been bringing the black holes into the public imagination in a new way. For decades, they had been the stuff of the chalkboard equations and the computer simulations. Now, for the very first time, the people could be looking at an actual image and be knowing that they were seeing the edge of a place where the known laws of the universe are breaking down. The smaller size of Sagittarius A star is meaning that the light, or more accurately the radio waves from its surrounding material, is having a much smaller target to be tracing. From the Earth, Sagittarius A star is appearing to be about the size of a donut that is sitting on the Moon. It is also more lively than M87*. While M87 times is changing over the timescales of the days to the weeks, Sagittarius A star is changing on the order of the minutes to the hours. The gas that is swirling around it is so close to the black hole that it is orbiting at the incredible speeds, and it is sometimes circling in just a few minutes. This is meaning that by the time that the astronomers are trying to be stitching together an image, the target that they are looking at has already been changing its shape. For M87 times, the glow of the disk is staying relatively stable during the observing window, which is making it easier to be producing a sharp image. For Sagittarius A star, it is like trying to be taking a long exposure photograph of a candle flame in the wind. The flickering is keeping on smearing the result. The atmosphere that is between the Earth and Sagittarius A star is adding yet another layer of complexity. M87 times is lying far outside of our own galaxy, so its radio waves are traveling mostly through the intergalactic space before they are reaching us. Sagittarius A star, on the other hand, is sitting inside of the crowded center of the Milky Way. The dust particles are scattering the radio waves, and they are blurring and distorting the view. Correcting for that blurring is requiring the heavy data processing, and even then, some of the fine detail is inevitably being lost. For M87 times, the observing campaign could be being spread out without too much concern. For Sagittarius A star, all of the participating telescopes had to be being synchronized with the extreme precision so that they were capturing the same, constantly changing target at the exact same moment. Even a short delay could be meaning that the data from one of the telescopes would be looking at a different version of the black hole than the others, and it would be ruining the image. The weather had been becoming a much more serious problem for this reason. The EHT network is including the observatories from Chile to Hawaii to the South Pole. For Sagittarius A star, all of these sites had been needing the clear skies at the same time over several days. And during the same short observing window when the black hole was in the right position in the sky, a storm in Chile or the clouds in Hawaii could be throwing off the entire schedule. Coordinating this was like planning a global concert where every single musician had to be playing the exact same note at the exact same instant, but where each of the stages was on a different continent and the instruments were extremely sensitive to the weather. The imaging process itself also had to be being rethought. The rapid variability of Sagittarius A star had been meaning that the traditional approach, which was treating the black hole as a static object, would not be working. The scientists had had to be developing the new algorithms to be handling a target that was morphing while they were trying to be observing it. Instead of a single stable image, they had been ending up generating the thousands of the possible images and be looking for the patterns that were remaining consistent across them. This had been the only way to be being sure that what they were seeing was real and that it was not an artifact of the changes that were happening during the observation. M87 times is surrounded by a steady inflow of gas that is producing a bright glowing ring. The accretion of Sagittarius A star is much weaker, which is meaning that less radiation is being emitted from its surroundings. This low brightness is making it harder to be getting a strong, clean signal. It is a bit like trying to be photographing a faint candle in the daylight compared to be photographing a campfire at night. The campfire, like M87 times, is naturally standing out. The candle, like Sagittarius A star, is getting lost in the noise unless the photographer is taking the extra care. At the shorter radio wavelengths, the scattering from the galactic plane is worse, and it is making the image blurrier. At the longer wavelengths, the scattering is less of an issue, but the resolution is decreasing, and the features of the black hole are becoming harder to be distinguishing. Finding the sweet spot in the wavelength choice was a balancing act between the resolution, the clarity, and the brightness. The stars, the clouds of gas, and the other radio sources are all lying in the same direction, and their signals can be overlapping. Separating these signals is possible, but only with the careful filtering and the cross-checking. This had been requiring the months of the analysis after the observations had been being completed, as the scientists had been painstakingly removing the unwanted background signals from the data. By the time that the final image of Sagittarius A star was ready, the scientists had been processing the petabytes of the raw data, and they had been running the thousands of the simulations, and they had been testing the countless variations of their imaging algorithms. Every single step had been being checked and rechecked to be making sure that the image was truly reflecting the structure of the black hole, and that it was not a byproduct of the methods that had been being used. When the picture had finally been being released in 2022, it had been showing the now familiar blurry ring, which was remarkably similar in its shape to that of M87 times, but it was fuzzier and more variable. Behind that fuzziness was the years of the work, and much of it was tackling the problems that had had no precedent. It is easy to be thinking of Sagittarius A star as a natural next step after M87*, but in many ways it was a leap. All of its issues had been combining to be making it one of the more stubborn targets in the modern astronomy. The success of its image was a demonstration of how the creative problem-solving, the coordination, and a willingness to be rethinking the established methods can be overcoming the challenges that at first are seeming to be insurmountable. When the image of Sagittarius A star was released to the public, it was celebrated as one of the most significant scientific achievements of the decade. But for the scientists, the photo was not the end of the journey. In many ways, it was just the beginning. The picture confirmed certain things that we had expected, but it also left us staring at a long list of questions that remain unanswered. The first and most obvious gap in our understanding comes from the fact that the image does not directly tell us how fast Sagittarius A star is spinning. Black holes can have different rotation rates, from no spin at all to the maximum that is allowed by the laws of physics. The spin affects the shape of the event horizon, the way that the matter orbits the black hole, and the power of any jets or energetic outflows. But determining that spin from a blurry averaged image is far from being simple. For M87 times, the scientists had had a better chance of narrowing down the spin because the black hole is changing much more slowly. The bright spots in the accretion flow of Sagittarius A star are constantly moving and reshaping the pattern of the light. When the EHT team had been compiling their final image, it had been an average of many different moments. This had been making it harder to be picking out the stable features that might be revealing the rotation. The spin might still be hiding in the data, and it might be waiting for a different kind of analysis, but it is not something that the first image could be telling us outright. The second major unknown is the orientation of Sagittarius A star. A black hole does not have a top or a bottom in the way that a planet does, but it does have an axis of rotation like a giant spinning sphere. Knowing the tilt of that axis relative to the Earth is important for understanding how the matter is falling, in how the energy might be being released, and how it is interacting with the rest of the galaxy. For M87 times, this was easier to be estimating because the black hole is producing a visible jet which is giving a clear directional clue. Sagittarius A star does not have a prominent jet that we can see. It might have some smaller outflows, but they are weak and they are hard to be detecting through the crowded, dusty center of the galaxy. Without that guiding line, the orientation is still uncertain. The image from the EHT had been taken in a way that had not directly been capturing the polarization of the light, which is one of the best indicators of the structure of the magnetic field. The follow-up observations are beginning to be focusing on the polarization, but for now, the exact shape and the strength of the magnetic fields that are around Sagittarius A star are remaining mysterious. The image that we had seen was an average, but what does Sagittarius A star be looking like at any given moment? If we could be taking the rapid snapshots instead of the long averages, then we might be seeing the hotspots that are orbiting very close to the event horizon, the patterns in the flow of the gas, or the flares that are bursting into view. These could be telling us much more about the behavior of the black hole. But to be getting a clear picture at such a fine resolution, the telescopes have to be collecting the data over many hours. The image also does not be telling us the full story of how much matter is actually being falling into Sagittarius A star. It does not be revealing the long-term feeding habits of this black hole. Even the shadow is raising the questions. The general relativity is predicting a certain size for the shadow based on the mass of the black hole. The image of Sagittarius A star is matching that prediction fairly well, but the margin of error is still large enough that the alternative theories of gravity are not entirely being ruled out. A more precise image might one day be tightening those limits, and it might be telling us if the space and the time are truly behaving exactly as the general relativity is describing. The light that we are detecting from Sagittarius A star at the radio wavelengths has already been being filtered and scattered by the turbulent clouds that are along the way. The astronomers are correcting for this, but there is always a chance that some of the subtle features are being blurred beyond the recovery. This is a part of why improving the resolution and working at the multiple wavelengths is so important for the future. These unanswered questions are central to be understanding what Sagittarius A star actually is and how it is behaving. The photo had been giving us a face for the black hole, but it had not been giving us its full identity. More of the observing runs with the EHT are being planned, and this time they will be including more of the telescopes to be improving the quality of the image. There is also an effort to be capturing the polarized light from the black hole. Longer of the observing campaigns might be helping us to be catching and be tracking the individual features in the accretion flow. Some of the researchers are even exploring the possibility of the space-based radio dishes that could be linking up with the ground-based ones, and they could be creating an Earth-to-orbit array with the much greater resolution. Each of these steps could be answering one or more of the questions that the first photo had been leaving hanging. But for now, the black hole that is at the heart of our own galaxy is remaining partly hidden both by the limits of our technology and by the nature of the object itself. Even with all of our advances, a single image, no matter how groundbreaking, cannot be capturing the full story of our own black hole. The inside of a black hole is less like an undiscovered country and more like a sealed box that can never be opened. Still, the theories are trying to be reaching inside, and they are using the mathematics and the laws of physics as the only tools that are available. The simplest of the ideas, which is being drawn from the classical physics, is saying that nothing is orbiting inside. Once the matter is crossing the event horizon, then it is moving inexorably toward the singularity without the possibility of being circling around it. In that picture, the space and the time themselves are so distorted that all of the paths are leading inward. But the modern physics is not stopping at this stark conclusion. It is asking whether the singularity is even real, or whether something else is taking its place when the quantum effects are becoming important. One of the possibilities is coming from the idea of the quantum gravity, where the known rules of the gravity are merging with those of the quantum mechanics. In such a framework, the singularity might be being replaced by an extremely dense but a finite structure. It would be unimaginably small, and it would be far tinier than an atom. but it could be holding all of the mass and the energy of the black hole in a strange quantum state. If that is true, then the space that is inside of the event horizon might be having the regions where the particles or the fields could, in the theory, be moving in the loops or the patterns, although to us on the outside, these orbits would be being hidden forever. Some of the researchers have been imagining that inside of a black hole there might be the entire zones where the physics is behaving differently. In certain of the speculative models, once you are passing the event horizon, then you could be encountering a kind of inner horizon, which is a second boundary that is marking a transition to another kind of the space-time. Inside of this region, it is being possible, at least in the mathematics, for the particles or even the light to be moving in the stable paths. In such models, the singularity is not a simple point, but a complicated structure that is sometimes being shaped like a ring. In that scenario, the orbiting inside is being possible, but it would be being nothing like the orbits that are around a star or a planet. Another idea is coming from the concept of the exotic matter, which are the forms of the matter that are obeying the rules that are unlike anything that we are knowing from the ordinary atoms. Some of the versions of the string theory are suggesting that the interior of a black hole could be being filled with the tangled networks of the strings or the membranes, and each of them would be vibrating at the different frequencies. Within such a bizarre environment, the movement might not even be following the traditional curve of an orbit. Instead, the objects could be being trapped in the repeating loops of the space-time, and they could be moving forward and backward in the ways that are having no equivalent in our everyday experience. The quantum mechanics is also introducing the possibility of the virtual particles, which are the brief appearances of the particle pairs that are winking in and out of the existence in the empty space. Near the event horizon, these virtual particles are playing a role in what is being known as the Hawking radiation, which is the theoretical process by which the black holes can be slowly losing the mass over the trillions of the years. If the virtual particles can be appearing just outside of the horizon, then could they also be existing inside? If so, then their fleeting lifespans and their strange behavior could be creating the complex interactions within the core of the black hole. In such a picture, you might be imagining a kind of seething, invisible ocean where the quantum fluctuations are swirling in the patterns that we would be calling the orbits if we could be seeing them, but they are being gone almost as soon as they are appearing. A more radical line of the thought is suggesting that the inside of a black hole might not even be a part of our own universe in the traditional sense. Some of the models are proposing that when the matter is falling in, then it is being funneled into a completely new region of the space and the time, and it is possibly even a new universe entirely. This is leading to the wormhole idea, which is the notion that some of the black holes might be connecting to the distant parts of our own universe, or even to the entirely separate universes. The mathematics for certain of the solutions of the equations of Einstein is allowing for the structures where the matter could be entering, and it could be following the curved paths inside, and it could then be emerging somewhere else. If a wormhole were to be stable, which most of the physicists are doubting, then it might be containing the zones where the movement is looking like the orbiting, but instead of circling a central mass, the objects would be being winding through the curved tunnels of the space-time. There is a line of the thought that is focusing less on the matter and more on the information. Some of the researchers who are studying the black hole information paradox, which is the puzzle of whether the information is being destroyed when it is falling into a black hole, are suggesting that the information could be being preserved in some form inside. If so, then these patterns could, in the theory, be changing and be interacting over the time, and they could be forming the cycles or the repeating behaviors. In the loop quantum gravity, which is a theory that is trying to be describing the space and the time as being made of the tiny discrete units, the space itself is having a kind of atomic structure. Inside of a black hole, these units might be arranging themselves in such a way that, instead of collapsing to a singularity, the matter is bouncing and is oscillating. This bounce could be leading to a dynamic interior where the certain regions are repeatedly swinging around the others. In such a model, the orbits could be a byproduct of the geometry of the space itself, and not of the gravity that is pulling on the matter in the usual way. Some of the cosmologists have been asking whether the black holes might be the seeds of the new universes with their interiors that are expanding in a way that is being invisible to the outside. If so, then the inside might be looking like a vast expanding cosmos with its own stars and the galaxies. From that point of the view, our own universe might have been beginning inside of a black hole in another universe. Of course, all of these ideas are facing the same ultimate barrier. The event horizon is not letting us be seeing inside. No matter how advanced our telescopes are becoming, the interior will be remaining hidden from the direct observation. The only way that we can be exploring it is through the mathematics, the simulations, and the indirect clues from how the black hole is interacting with the space that is around it. But that is not stopping the scientists from asking the question, because sometimes the act of imagining what could be inside is as important as finding the answer. It is forcing us to be testing the limits of our theories and to be thinking about the nature of the space, the time, and the reality itself in the ways that we never would otherwise. The evidence that Sagittarius A star is a supermassive black hole is seeming to be overwhelming. The stars are whipping around an invisible point at the extreme speeds. Their paths are being shaped by a gravitational pull that cannot be explained by the ordinary matter. The light that is coming from the nearby gas and the dust is matching what is being expected from the material that is being heated to the extreme temperatures as it is falling towards an event horizon. But in the science, the assumptions are always being tested. And for something that is as strange and as important as a black hole, the alternative ideas have been put on the table. Some of the researchers have been asking the question, what if Sagittarius A star is not a black hole at all? What if it is something that is even stranger? The first of the alternatives that is coming up is the dark matter. The dark matter is not emitting, absorbing, or reflecting the light, which is making it impossible to be detecting directly. We are only knowing that it is there because of its gravitational effects on the galaxies and the galaxy clusters. It is holding the cosmic structures together, and it is making up most of the matter in the entire universe, yet it is remaining unidentified. Could Sagittarius A star be a massive concentration of the dark matter? On the surface, it might be seeming to be plausible. The dark matter could, in the theory, be clumping into a dense region at the center of the galaxy. Its gravity could still be pulling on the stars in the same way that we are observing. But there is a problem. The dark matter is not seeming to be interacting much with itself, and it is not losing the energy by radiating the heat or the light in the way that the normal matter is doing. Without a way to be shedding the energy, it would not be collapsing into a small dense core like we are seeing in Sagittarius A star. It would be staying spread out, and our observations are showing that whatever is in the center of the Milky Way is incredibly compact. It is so compact that it is fitting inside of a space that is smaller than our own solar system. That is far too dense for any of the known forms of the dark matter to be achieving. Still, some of the researchers have been considering that maybe there are the types of the dark matter that we have not been discovering yet, the particles that are interacting with each other more strongly. If such particles were to be existing, then perhaps they could be clumping together into something that is as dense as a black hole without actually forming an event horizon. These hypothetical dark matter structures would be invisible, but they might not be behaving exactly like the black holes. They could be having a solid or a fuzzy surface, and anything that was falling onto them would be hitting that surface rather than be disappearing forever. The challenge is that no observation so far has been showing the signs of such a surface. Everything that is falling towards Sagittarius A star is seeming to be vanishing completely from the view, just as if it were to be crossing an event horizon. Another of the alternative ideas is the boson star. This is one of the more exotic of the proposals, and it is coming from the world of the particle physics. The bosons are the particles that are following the different rules than the particles that are making up the normal matter. The photons, which are the particles of the light, are the bosons. The Higgs particle is a boson. Some of the theories are suggesting that there could be a new kind of the boson, which is ultra-light and is extremely stable, and that it could be forming the gigantic clouds in the space. Under the right conditions, such bosons could be collapsing into a very dense star-like object without being forming a black hole. A boson star would be having no hard surface, but it also would not be having a true event horizon. Instead, the light that was passing near it would be bending in the strange ways, and the material that was falling toward it might be slowing down rather than be disappearing completely. If Sagittarius A star were to be a boson star, then its image might be looking very similar to that of a black hole at the resolutions that we are currently having. The shadow in the famous photo could still be appearing because the light would be being bent and be being redirected around it, and it would be creating a dark, central region. But there could be the subtle differences. The differences in how the brightness is changing over the time, or in how the matter is moving close to the object. Detecting those differences would be requiring the sharper images and the more precise timing measurements than we are having today. Then there is the gravastar, which is a concept that was born from the attempts to be avoiding the singularity problem in the black holes. Some of the physicists are being deeply uncomfortable with the infinities in their equations. In the late 1990s, the idea of the gravastar was being proposed as a way around this. Instead of collapsing into a singularity, the core of a dying star might be going through a phase transition which is like the water that is turning into the ice, and it could be creating a shell of the exotic matter. Inside of that shell, the space would be being filled with a strange form of the energy, and it could possibly be the same kind that is driving the expansion of the universe. From the outside, a gravastar would be looking almost exactly like a black hole. It would still be bending the light in the same way, and the orbits of the stars that were around it would be being indistinguishable from those that were around a true black hole. But there would be being no event horizon, and it would just be a surface that was just barely beyond the point where the light could be escaping. If Sagittarius A star were to be a gravastar, then the falling material would not be vanishing forever. Instead, it might be slamming into the surface, and it could be releasing a sudden flash of the energy. Detecting such a flash could be proving the idea of the gravastar, but no such flash has ever been being observed. One of the reasons could be that the infall of the matter is too steady and too faint to be producing a visible burst. Another is that our telescopes are not being sensitive enough to be catching it. Either way, the gravastar is remaining in the category of the possible but the unproven. There are even the wilder ideas. Some of the scientists have been speculating about the fuzzballs which are coming from the string theory, and are suggesting that the black holes might be being made entirely of the tangled strings of the fundamental energy. In this view, there is being no empty space inside of a black hole, and there is being no singularity, and there is just a messy ball of the strings that from far away is looking like a black hole. Others have been proposing that the black holes might be the mouths of the wormholes. If that were to be the case, then it would be making the center of our own galaxy a gateway. These ideas are almost entirely speculative, but they are remaining on the edges of the theoretical discussion because the black holes are still leaving us with so many of the unanswered questions. The problem with testing any of these alternatives is that for all of the practical purposes, Sagittarius A star is behaving exactly like a black hole. The observations so far have been being consistent with the model of the black hole, and none of them have been showing a clear signal that would be pointing to a boson star, a gravastar, or any other of the exotic objects. Yet the science is working best when it is keeping on questioning, and when it is leaving the room for the possibilities that might at first be seeming to be unlikely. Each of the new observations is bringing us a little bit closer to be seeing into the true nature of one of the most mysterious places in the entire galaxy. And until the evidence is so strong that all of the other possibilities are fading away, the question will be remaining, are we certain about what is really being hiding at the very heart of the Milky Way? Or have we only begun to be scratching the surface. The central region of the Milky Way is very different from the calm suburbs of the galaxy where our own sun is residing. The stars that are near Sagittarius A star are moving at the incredible speeds, and they are sometimes completing an orbit in just a few years. The gravitational field in this inner zone is intense, and this concentration of the gravity could have been influencing how the matter had been collecting in the earlier stages of the life of the galaxy. When the Milky Way was young, which was over 13 billion years ago, it was not a smooth, elegant spiral. It was messy, and it was filled with the clumps of the gas, the dust, and the small proto-galaxies that were merging together. In those chaotic times, the seeds of today's structures were forming. Sagittarius A star had likely been beginning as a much smaller black hole, and it was perhaps the remnant of one of the first massive stars. Over the time, as the gas and the stars had been falling toward the center, the black hole had been growing. Its gravity may have been helping to be pulling the matter inward, and it may have been deepening the central potential well and be encouraging the buildup of the dense bulge that we are seeing today. The simulations are suggesting that even in those early days, a central black hole could be stirring the surrounding gas. This movement of the gas could be having two very different effects. In some of the cases, it might be funneling the material toward the center, and it might be feeding the black hole and be helping the bulge to be forming faster. In the other cases, if the black hole had been becoming active, then it could be blowing the gas outward, and it could be halting the star formation in the certain areas. Which of the effects is dominating is depending on how fast the black hole is growing and how much energy it is releasing. The astronomers have been observing that many of the large galaxies are having the central black holes whose mass is being directly related to the mass of the bulge of the galaxy, which is the dense central region of the stars. This relationship is suggesting that the black holes and the bulges are growing together. While this is not proving that Sagittarius A star had been shaping the Milky Way, it is hinting that its growth and the growth of the galaxy had been being connected in some way. If Sagittarius A star did be having a strong influence in the past, then it had likely been happening during the periods when it was much more active. In that state, it would have been pumping the huge amounts of the energy into its surroundings. Such activity could have been preventing the certain areas from forming the stars too quickly, and it could have been allowing the spiral structure to be evolving over a longer period. The Fermi bubbles are showing that the reach of the black hole is not just local, it could be affecting the halo of the galaxy as well. The events like that might have been playing a role in shaping the overall distribution of the matter in the Milky Way. The gravitational pull of Sagittarius A star is being strongest close to the center, but it is gradually fading with the distance. However, the central mass concentration, which is including both the black hole and the dense star cluster that is around it, may have been helping to be maintaining the stability of the bar structure of the Milky Way, which is a long, bright band of the stars that is cutting across the center and is funneling the material inward. This bar could be being important for feeding the gas into the inner regions, both for the star formation and for the own growth of the black hole. It is also being possible that Sagittarius A star had been influencing the chemical evolution of the Milky Way. By controlling where and when the stars had been forming, it could be indirectly affecting how the heavy elements had been being spread through the galaxy. In the places where the activity of the black hole had been clearing out the gas, the star formation might have been pausing, and it might have been delaying the recycling of the elements like the carbon, the oxygen, and the iron into the new generations of the stars. Over the billions of the years, this could be contributing to the variety of the chemical compositions that we are seeing in the different parts of the galaxy today. Still, there are the limits to how much impact a central black hole can be having. The Milky Way is enormous, and its outer disk is lying so far from Sagittarius A star that its gravity is barely being noticeable there. The spiral arms where our own sun is residing are being shaped more by the density waves that are moving through the disk than by anything that is happening at the core. This is meaning that while Sagittarius A star might have been influencing the inner structure and the bulge, the sweeping arms of the galaxy had likely been developing through the other processes. The early Milky Way has long since been changing beyond the recognition, and much of the evidence is being buried in the motions and the compositions of the stars that we are observing today. By studying the other galaxies at the various stages of the growth, the researchers are hoping to be finding the snapshots of what ours might have been looking like billions of years ago. And in those snapshots, they are seeing the fingerprints of the central black holes that are shaping their hosts. Some of the models are suggesting that without a central black hole, the Milky Way might have been ending up with a very different appearance, and it might have perhaps been having a smaller bulge or a less organized inner structure. Others are arguing that while the black holes and the galaxies are growing together, the influence of the black holes is more of a feedback loop than a master plan. In this view, Sagittarius A star had been shaping the heart of the Milky Way, but the overall form of the galaxy had been coming from a mix of the gravity, the rotation, and the slow settling of the matter over the cosmic time. The truth may be being somewhere in between. Sagittarius A star was likely being both a passenger and a driver in the story of the Milky Way. At the times, it may have been a quiet observer, and it may have been letting the galaxy be evolving naturally. At the other times, it may have been sending the ripples of the energy and the motion through the heart of the Milky Way, and it may have been leaving the marks that we can still be tracing today. Around the entire world, the engineers, the astronomers, and the computer scientists are working on the next stage of the instruments that will be making the EHT be looking like an early prototype. The picture of Sagittarius A star that we are having today is the product of the incredible cooperation. But it was also being made with the technology that is already being years old. In the astronomy, there is always a delay between the moment that the data is being collected and the moment that the results are being published. By the time that the image of the central black hole of our own galaxy had been being released, the tools that had been being used to be creating it were already on their way to be being improved. The biggest step forward will be coming from adding more of the telescopes to the network. The more of the stations that you are having, the sharper the image is becoming. Right now, there are the gaps in the virtual mirror of the EHT because you can only be placing the telescopes in the certain locations where the terrain, the funding, and the political agreements are allowing it. Adding the new sites in the parts of the world where there are no current EHT stations would be filling in those gaps, and it would be giving the astronomers a more complete view of Sagittarius A star. One of the plans is to be placing the new radio dishes in Africa, which would be helping to be covering the southern hemisphere sky more evenly. Another of the proposals is involving installing the additional stations in the Pacific Islands, or even at the sea, and it would possibly be on the ships or the floating platforms. These would be catching the parts of the radio wave patterns that the current telescopes are missing. Each of the new locations is increasing the detail that we can be recovering from the light that is around the black hole. There is also the talk of moving some of these observatories into the space. This is one of the most exciting of the possibilities. The space-based radio telescopes could be orbiting the Earth or even be traveling farther out, and they could be creating a virtual dish that is larger than the Earth. This space VLBI has been being tested before, but not yet for something that is as challenging as imaging a black hole. A space-based dish that was working with the ground-based telescopes could be increasing the resolution so much that we might be able to be seeing the changes in the shape of Sagittarius A star over just a few hours or the days. Another of the major leaps will be coming from the improvements in the way that the data is being handled. The current EHT is using an enormous amount of the data. The future systems will be using the faster, higher capacity recording, and they may even be allowing the direct streaming between the sites by using the ultra-high-speed connections. This would be letting the astronomers be combining and be processing the data in near real time, rather than be waiting for the months for the result. The processing power is also getting a boost. The computers that are turning the raw signals of the EHT into an image are already being impressive, but the next generation will be using the more advanced algorithms. Some of them will be being driven by the machine learning. These systems can be recognizing the patterns in the interference data faster and more accurately than the human-made software, and they can be producing the clearer, more reliable images. The artificial intelligence could also be helping to be detecting the changes in the surroundings of the black hole more quickly, and it could be flagging the interesting events as they are happening. Even the way that the telescopes are looking at Sagittarius A star will be changing. Right now, the EHT is observing at a single radio wavelength of 1.3 millimeters. This is a sweet spot for passing through the atmosphere of the Earth, with the minimal interference, but it is only one slice of the spectrum. By observing at the multiple wavelengths at once, the astronomers could be getting more of the information about the material that is around the black hole, its temperature, and how the different layers of the gas and the plasma are moving. The addition of the shorter wavelengths, like 0.87 millimeters, would be sharpening the image further, but it would also be requiring the extremely precise equipment to be handling the smaller, more fragile signals. The longer wavelengths could be revealing the cooler gas that is farther from the event horizon, and they could be giving a fuller picture of the environment. The next phase of the EHT will likely be including more of this multiband observing, and it will essentially be giving us the color images of the black holes, even though they will not be looking like the colors to the human eye. The future instruments may also be observing for the longer stretches of the time. The first EHT image of Sagittarius A star was being based on only a few nights of the observations, because all of the telescopes had to be being in the clear weather at the same time. The new scheduling and the weather prediction methods will be helping to be capturing more of the data. The more that we are observing, the more that we can be tracking the changes in the surroundings of the black hole. This could be leading to the movies of the material that is moving around Sagittarius A star, and they could be showing the swirling plasma in the motion. One of the most ambitious of the concepts is to be combining the EHT with the other types of the telescopes entirely. For example, the upcoming square-kilometre array in Australia and South Africa will be the largest radio telescope that has ever been being built, and it will be covering the huge areas with the thousands of the smaller antennas. While it is not being designed specifically for imaging the black holes at the resolution of the EHT, it could be being linked into the network to be adding the sensitivity that would be allowing the fainter features to be being detected, such as the smaller flares or the thin streams of the plasma. In the far future, some of the astronomers are dreaming about being using the telescopes that have been placed on the Moon for the work of the EHT. The lack of the atmosphere of the Moon would be allowing the radio observations without the distortions that the air of the Earth is creating, and the telescopes there could be operating around the clock without the daylight cycle being interrupting the observations. A lunar station that was being paired with the Earth-based sites would be making the virtual dish enormous, and it would be sharpening our view dramatically. The first image of M 87 times had been including a polarization map that was showing the magnetic field lines that were around the black hole, and the similar work is being done for Sagittarius A star. The improved polarization data could be revealing how these fields are twisting, breaking, and reconnecting, and it could be offering the clues about why Sagittarius A star is being relatively quiet. The new instruments will also be making it easier to be comparing Sagittarius A star to the black holes in the other galaxies. If we can be getting the equally sharp images of the multiple black holes, then we can be starting to be seeing the patterns. Whether the size, the spin, the feeding rate, or the magnetic activity is determining their appearance and their behavior. The first picture from the EHT was a milestone, but it is almost certain to be being replaced by a clearer, sharper image before long. If the upgrades are succeeding, then the next generation of the images of the black holes will not just be showing us a still frame, they will be letting us be watching the most mysterious object of our own galaxy in the action. The speed of the spin of Sagittarius A star could be telling us a great deal about its history. Whether it had been growing slowly by eating the small bits of the matter over the billions of the years, or whether it had been gulping down the large amounts all at once, and it could possibly have been in the violent mergers with other black holes. The problem is that the spin is not something that we can be seeing directly, We have to be inferring it from the way that the light and the matter are behaving near the black hole. And one of the most promising of the ways to be doing that is through a method that is called the X-ray polarimetry. The polarimetry is measuring the orientation of the light waves. The light is being made up of the electromagnetic waves that can be vibrating in many of the directions. But the certain physical processes, such as the scattering off of the particles or the moving through the magnetic fields, can be causing those vibrations to be aligning in the particular ways. When we are measuring that alignment, then we are gaining the clues about the environment that the light has been passing through. In the case of Sagittarius A star, we are being interested in the polarization of the X-rays that are being emitted from the matter as it is spiraling into the black hole. These high-energy photons can be carrying the fingerprints of the spin of the black hole, and they can be being hidden in their polarization pattern. The matter that is falling towards Sagittarius A star is heating up, and it is producing the X-rays. These X-rays are bouncing around in the warped space that is near the event horizon, and they are being influenced by both the gravity and the magnetic fields. If the black hole is spinning, then it is dragging the space itself around with it, which is a phenomenon that is called the frame dragging. This twisting of the space-time is changing the paths that the X-rays are taking, how they are scattering, and how their electric fields are being oriented when they are finally escaping to us. By studying exactly how polarized these X-rays are, we can be backtracking and be determining not only the geometry of the material that is swirling in, but also the rate of the spin of the black hole. Up until recently, the X-ray polarimetry was a dream more than a reality. While we have been being able to be measuring the X-rays for the decades, measuring their polarization is much harder. The instruments are needing to be detecting not just the energy and the direction of each of the photons, but also the orientation of its electric field. This is requiring the incredibly sensitive detectors and the very stable platforms. On the Earth, the X-rays from the space are being absorbed by the atmosphere, so the polarimetry must be being done from above the air, and it is either from the satellites or the high-altitude balloons. The Imaging X-ray Polarimetry Explorer, or 9XPE of NASA, which had been being launched in December of 2021, is one of the first of the dedicated missions for this purpose. IXPE is already being collecting the polarization data on the various cosmic objects, the pulsars, the supernova remnants, and the distant active galaxies. Sagittarius A star is a challenging target because it is relatively faint in the X-rays compared to the more active black holes, but IXPE is having the precision to be attempting it during the flares. In those brief moments, the polarization signal could be being strong enough to be giving us a reading. The concepts for the next generation are including the instruments with the larger collecting areas to be gathering more of the X-ray photons, the higher resolution to be separating the emission of the black hole from the crowded galactic center, and the faster timing capabilities to be tracking the changes in the polarization during a flare in real time. These improvements could be allowing us to be watching the polarization angle be swinging as the matter is orbiting near the event horizon, which is an effect that could be revealing not only the spin but also the tilt of the rotation axis of the black hole relative to the galaxy. A fast-spinning black hole can be storing the enormous amounts of the rotational energy which can be being tapped to be powering the jets and the winds. Even though Sagittarius A star is not having a major jet today, its spin might still be a hidden engine that is influencing the dynamics of the gas that is around it. The spin could also be a fossil record of the past events. If the spin is high and is being aligned with the galactic plane, then it might be meaning that Sagittarius A star had been growing mostly by pulling in the matter from the disk of the galaxy. If the spin is low or is being tilted at a strange angle, then it might be meaning that it was being involved in the chaotic mergers and it was swallowing the other black holes that had been coming in from the odd directions. There is also the question of whether the spin can be changing over the time. If Sagittarius A star is about to be entering a more active phase, as some of the recent flaring behavior is suggesting, then the new infalling material could be either spinning it up or be slowing it down, and it would be depending on the direction of its angular momentum. The polarimetry is offering a way to be tracking this evolution over the years or the decades, and it is turning the spin from a fixed property into a dynamic measurement. The spin measurements are also feeding into our understanding of the general relativity in the strong gravity regime. The equations of Einstein are making the specific predictions about how a spinning black hole is warping the space-time and is polarizing the light. If the results of the polarimetry are disagreeing with those predictions, then it could be signaling the new physics. Perhaps the geometry that is near the event horizon is not exactly what the general relativity is describing, or perhaps the quantum effects are playing a role. Another of the interesting twists is that the polarization could be helping to be separating the effects of the gravity from those of the magnetic fields. Near a black hole, these two influences are being intertwined. The gas that is spiraling in is carrying the magnetic fields with it, and those fields can be twisting, be reconnecting, and be releasing the energy. The magnetic fields can also be polarizing the light, but in a different way than the gravity is doing. By comparing the polarization at the different X-ray energies, the scientists can be trying to be disentangling the two effects, and they can be leading to a clearer picture of the environment of the black hole. Long term, we might even be seeing the interferometric X-ray polarimetry. This could be giving us the polarization maps at the extremely fine resolution, and it could perhaps be showing which of the parts of the accretion flow are contributing most to the signal. For Sagittarius A star, that could be meaning being identifying where the X-rays of the flares are actually coming from a hot spot that is orbiting very close to the event horizon, a shock front in the accretion flow, or some magnetic reconnection event. As the tech is advancing, the polarimetry may be becoming as routine as measuring the brightness or the spectrum. For now, though, it is on the cutting edge, and it is a technique that could be opening a new dimension in our study of the black holes. In the case of Sagittarius A star, it is offering a rare and a precise way to be peering into its hidden history. We may not be being able to be sending a probe into the black hole, but by studying the subtle patterns of the X-ray polarization, we might be reading the story that has been being written in the twists of the space-time. A stable black hole like Sagittarius A star, which is one that is not merging with another object, is not creating the gravitational waves that are strong enough for us to be detecting. The space that is around it is being distorted, yes, but it is not changing fast enough to be producing the ripples that we can be picking up. For the gravitational waves to be being generated in a way that we could be measuring, something dramatic has to be happening. That might be meaning a smaller black hole that is spiraling into Sagittarius A star, or a massive star that is being torn apart, or even two black holes that are merging in the galactic center. One of the most promising of the scenarios is what the scientists are calling an extreme mass ratio in spiral, or EMRI. This is when a much smaller object, which is like a star or a black hole that is a few tens of times the mass of the Sun, is getting caught in the gravitational grip of Sagittarius A star, and it is slowly spiraling inward over the thousands or even the millions of the years. As it is falling closer, it is moving faster, and the distortions in the space-time are growing more intense. Near the end, in the final years, or the months before it is crossing the event horizon, the smaller object would be producing the gravitational waves with a signature that is unlike anything else in the entire universe. These signals would be being too low in the frequency for our current ground-based detectors like LIGO or Virgo to be picking up, because their mirrors and their lasers are being tuned for the higher frequency events like the collisions of the stellar mass black holes. But a future space-based gravitational wave observatory, such as the planned LISA mission of the European Space Agency, would be being able to be hearing them. LISA, which is short for the Laser Interferometer Space Antenna, is being designed to be detecting the gravitational waves in the millihertz range, which is exactly the kind of slow, deep rumble that an EMRI would be producing as a small object is falling into a supermassive black hole. Instead of being using the mirrors on the Earth, LISA will be having the 3 spacecraft that have been placed millions of the kilometers apart in the space, and they will be being linked by the laser beams. This huge separation is allowing it to be sensing the long drawn-out distortions that are being caused by the massive objects that are orbiting each other slowly. If a stellar mass black hole or a neutron star is ever being caught in the death spiral towards Sagittarius A star, then LISA could, in the theory, be detecting it years before the final plunge. That would be giving the astronomers the time to be preparing and be coordinating the observations with the telescopes across the entire spectrum from the radio to the X-rays to be watching the drama be unfolding. There is also the possibility of being detecting the gravitational waves from the more exotic events, such as a sudden collapse of a massive star into a black hole near the galactic center, or the shattering of a neutron star under the extreme tidal forces. These would be being short-lived, but they would be being extremely violent, and they would be producing the high-frequency waves that our current detectors could be picking up. However, these events are rare, and they are unpredictable, and we would have to be being extraordinarily lucky for one to be occurring close enough to Sagittarius A star while our instruments are running. If we could be detecting the gravitational waves from Sagittarius A star, then the scientific payoff would be enormous. We could be measuring its mass and its spin with the incredible accuracy which is far beyond what is being possible by using the light alone. We could also be testing the general relativity in the strongest gravitational field that is being accessible to us. If the signal were to be showing any deviation from what the theory is predicting, then it could be pointing to the new physics, and it could perhaps even be revealing something that is unexpected about the nature of the space-time near the event horizon. One of the particularly intriguing of the aspects is that the gravitational waves could be giving us a direct sense of what is happening in the region that is immediately outside of the event horizon without being blocked by the gas, the dust, or the magnetic fields. The light can be being scattered, absorbed, or distorted, but the gravitational waves are passing through the matter almost unaffected. This is meaning that if we are wanting a clean, unfiltered view of how Sagittarius A star is interacting with its surroundings, then the gravitational waves could be becoming one of our most important of the tools. Detecting the gravitational waves from such events is requiring not only the highly sensitive instruments, but also the years of the continuous observation. The signals are often being buried in the noise, and they can be lasting for the months or the years, which is requiring the precise data analysis to be extracting them. The timing has to be being perfect, especially if we are wanting to be coordinating the gravitational wave detections with the traditional telescope observations. This is why the projects like LISA are being planned for the 2030s or later. There is a lot of the engineering and the testing to be being done before we can be operating such a delicate instrument in the space. The ground-based detectors are also being upgraded. The next of the generations, like the Cosmic Explorer in the United States and the Einstein telescope in Europe, are aiming to be being more sensitive than anything that we are having today. While they will not be being able to be catching the slow spirals into Sagittarius A star, they could be detecting the shorter bursts from the sudden, massive disruptions that are near the galactic center. Combining their data with the space-based detectors could be giving us a complete picture that is covering both the low and the high-frequency ends of the gravitational wave spectrum. Looking ahead, it is being possible that one day we will be having a network of the gravitational wave observatories in the space, much like how the radio astronomers are using the VLBI method to be linking the telescopes across the Earth. With the multiple space-based detectors that have been positioned at the different points in the solar system, we could be triangulating the source of the waves with the incredible precision, and we could be pinpointing exactly where in the galaxy they are coming from. That would be making it possible to be targeting Sagittarius A star in real time with the optical, the infrared, and the X-ray telescopes whenever something unusual is happening. The idea of being listening to the heartbeat of the central black hole of the Milky Way is still in the realm of the future, but it is no longer being pure science fiction. The technology is being developed, and the first of the steps toward detecting such signals are already being underway. If and when that day is coming, then we will not just be seeing Sagittarius A star through the lens of the light. We will be feeling its movements through the subtle tremors that it is sending across the very fabric of the universe. In the far future, a great cosmic event is awaiting our own galaxy. In about 4 billion years, the Milky Way will be meeting the Andromeda galaxy. The two of them are moving toward each other at a speed of roughly 110 kilometers per second. On the human scales, that speed is extraordinary. But in the vastness of the space, this slow drift is enough to be setting up one of the most dramatic events in the galactic history. At the very heart of this future encounter will be being two supermassive black holes, Sagittarius A star in our own galaxy, and the black hole that is at the center of the Andromeda galaxy, which is known as M31*. When we are thinking about a collision between the galaxies, it is being tempting to be imagining the stars that are smashing into each other like the billiard balls. But the stars are so far apart that even in a violent merger, almost all of them will be passing by without any direct contact. The true drama will be being in the way that the gravity is rearranging everything. The sweeping arcs of the gas clouds, the twisting of the spiral arms, the disruption of the stellar orbits, and the slow but the unstoppable migration of the central black hole of each of the galaxies toward the other. Over the millions of the years, these two titans will be being drawn together, and they will be falling toward each other through a process that is called the dynamical friction. This is where the background of the stars and the dark matter is acting like a drag, and it is robbing the black holes of the momentum until they are spiraling inward. Sagittarius A star will not be staying passive during this process. The influx of the gas, the dust, and the disrupted stars from the collision will be being like the fuel that is pouring into its surroundings. The same will be happening to the black hole of Andromeda. Both of them could be flaring into the active galactic nuclei, and they could be outshining the entire galaxies with the radiation from the matter that is falling toward their event horizons. If this is happening, then the night skies of any of the worlds that are still being present in the merging galaxies could be being lit by the two blazing points in the cosmic core, and each of them would be being far brighter than any of the stars. The structure of the Milky Way will not be surviving intact. As the galaxies are merging, their disks will be being stretched, pulled, and eventually be being transformed into something that is new, and it will likely be an elliptical galaxy with the less defined arms and a more spherical distribution of the stars. The stars that had once been orbiting in the neat, nearly circular paths around the center of the Milky Way will be being thrown into the random orbits, and some of them will be being ejected entirely into the intergalactic space. For the planets that are around the certain stars, the gravitational chaos might be dislodging them from their home systems, and it might be turning them into the lonely wanderers that are drifting between the galaxies. In the center, the slow dance that is between Sagittarius A star and M31 will be continuing, and they will be drawing closer with every single orbit. For the tens of the millions of the years, they will be orbiting each other at the decreasing distances, and they will be sending out the gravitational waves that would be being detectable by the instruments that are far more sensitive than anything that we are having today. These waves would be carrying away the energy, and they would be causing the pair to be spiraling inward faster and faster. In their final approach, the two event horizons will be meeting and be merging in a burst of the gravitational energy that is unlike anything that our own galaxy has ever been knowing. This merger will not only be reshaping the core of the new galaxy, but it will also be giving it a single, even more massive black hole. The final mass could be being tens of the millions of the times greater than our own sun, and it could perhaps even be approaching 100 million solar masses, and it would be depending on how much matter is falling in during the process. The spin of this new black hole will be being set by the orbital motion and the spins of the two original giants, and it will be meaning that the entire history of both of the galaxies will be being written into the way that this monster is rotating. For the life, if it is still being existing anywhere within the combined galaxy, the impact will be depending heavily on the distance from the center. Close to the merging black holes, the radiation from the infalling matter could be sterilizing the planets or be stripping away the atmospheres. But farther out where most of the stars will be ending up, the changes might be being more subtle. There will be the altered night skies, the shifted constellations, and the gradual fading of the spiral patterns that had once been defining the beauty of each of the galaxies. Even though this collision will be being far in the future, the astronomers are already studying the galaxy mergers that are happening elsewhere in the universe to be getting a preview of our own fate. The telescopes have been capturing the images of the galaxies in the various stages of the merging, from the first gentle tug of the gravity to the final coalescence into a single shape. These cosmic snapshots are telling us that the process is very slow and that it is taking hundreds of the millions of the years from the first contact to the complete union. It is less a crash and more a cosmic blending with the two galaxies that are becoming ever more entangled until they are being inseparable. The simulations are suggesting that our own sun, assuming that it has not yet been expanding into a red giant and been destroying the Earth, may be ending up in a completely different part of the merged galaxy. It could be being flung to the outskirts, and it could be being far from the core, or it could be drifting inward, and it would be depending on the gravitational interactions that it is experiencing during the merger. Either way, the galaxy that we are calling home will be being unrecognizable, and its central black hole will no longer be being the familiar Sagittarius A star, but a far larger and a more powerful descendant. The Andromeda collision will be being one of the few events that is capable of being waking Sagittarius A star from its current quiet state for a truly extended period. The sheer volume of the material that is being funneled toward the center will be ensuring a long-lasting phase of the high activity. The jets of the high-energy particles could be erupting from its poles, and they could be being powered by the twisting magnetic fields that are around its accretion disk. The brightness in the X-rays, the radio waves, and the visible light could be spiking to the levels that would be making the center of the galaxy an overwhelming beacon. From a cosmic perspective, this is not a destructive end, but a natural evolution. The galaxies are growing by merging. The Milky Way itself is the product of the countless earlier collisions, though most of them were with the much smaller companions. The meeting with the Andromeda galaxy is simply the next step on a much grander scale. Sagittarius A star has already been surviving the billions of the years of the galactic history. In 4 billion more, it will be taking part in one of the most spectacular transformations in the entire universe, and it will be binding two vast star systems into one. When the Milky Way and the Andromeda galaxy are colliding in 4 billion years, and their black holes are spiraling into one another in a dramatic finale, will there being anyone here on the Earth to actually be seeing it be happening? 4 billion years is an unimaginably long time. For the perspective, that is almost the same amount of the time that has been passing since the life had first been appearing on the Earth. Over such a span, the position of the Earth in the space will not be being fixed, and neither will the behavior of the Sun be remaining constant. Our own star is slowly growing brighter over the time, which is a natural part of its life cycle. In another 1 to 2 billion years, it is being expected that the increased energy output of the Sun will be causing the climate of the Earth to be changing in the extreme ways. The oceans may be beginning to be evaporating, and the atmosphere could be losing the water to the space, and the surface conditions could be growing too harsh for the life as we are knowing it. Long before the galaxies are colliding, our own planet may have already been losing its habitability. Even without the changes of the Sun, the gravitational reshaping of the Milky Way during the collision will be scattering the stars into the new orbits. The solar system is likely to be being tossed into a different position within the merged galaxy. We may be being pulled closer to the galactic core, where the radiation and the gravitational disturbances are stronger, or we might be being pushed farther into the outskirts. These shifts could be changing the long-term stability of the orbit of the Earth. In the best-case scenario, the solar system is remaining relatively untouched. and it is just drifting into a new neighborhood in the stars. In the worst case, the interactions with the passing stars could be nudging the planets into the new paths, or they could even be flinging them into the interstellar space. The process of the galactic collision itself is not meaning that the planets will be smashing into one another. Instead, the danger is coming from the gravitational tug-of-war as the two galaxies are passing through each other multiple times before they are fully merging. Every single close pass is rearranging the orbits of the countless stars. If our own solar system is being unlucky enough to be being near the path of another star during one of these passes, then even a slight change in the gravity could be disturbing the delicate balance that is keeping the Earth be circling the Sunday. If the Earth was to be somehow being sent drifting into the interstellar space, and it was to be being cut off from the warmth of the sun, then it would be becoming a frozen, airless world almost immediately. The only heat would be coming from the interior of the planet, and it would be slowly radiating away into the darkness. The life, if any were to be still being existing, would be being confined deep underground near the geothermal vents. From such a world, the collision of the galaxy might be being visible as a slow-motion ballet of the light in the sky, but no one on the surface would be seeing it. In around 5 billion years, the sun will be exhausting the hydrogen fuel in its core, and it will be swelling into a red giant. When that is happening, then its outer layers could be engulfing Mercury and Venus, and it could possibly be engulfing the Earth as well. Even if our own planet is avoiding being swallowed, then the sheer heat and the radiation would be destroying its surface and its atmosphere. By the time that the central black hole of the Milky Way is merging with that of Andromeda, our own sun may have already been being transformed into a white dwarf, and it may have been leaving the Earth a scorched and a lifeless husk. The humanity has only been being here for a tiny fraction of the history of the Earth, and it is being impossible to be knowing whether any of the intelligent descendants, the human or the otherwise, will be remaining billions of the years from now. The civilizations are rising and are falling on the scale of the thousands of the years, and the survival of the life on the Earth is depending on the countless factors. The humanity, or whatever species is replacing us, might have been being spread to the other planets, the other star systems, and even the other galaxies. If that is the case, then the witnesses to the galactic collision and the final merging of the black holes may not be being standing on the Earth at all. Still, there is a slim chance that the Earth itself could be remaining in a stable orbit and be avoiding the worst of the effects of both the evolution of the Sun and the gravitational chaos of the galactic merger. In that rare outcome, the night sky during the collision would be being unimaginably beautiful. Over the millions of the years, the Andromeda galaxy would be growing larger and brighter, and it would eventually be filling much of the sky with a haze of the stars, the glowing gas, and the dark dust lanes. The sight would be being breathtaking. No telescope would be being needed. When the two galaxies are fully merging, then the view might be being a tapestry of the light that is stretching from the horizon to the horizon. The merged core would be shining brilliantly, where Sagittarius A star and the black hole of Andromeda are whirling toward each other. The black holes themselves would be being hidden by the vast clouds of the gas and the dust, but their influence could still be being seen in the form of the powerful jets and the bursts of the energy as the matter was spiraling toward them. These outbursts might be briefly outshining every single star in the entire galaxy combined. The night sky would not just be being beautiful, it would be being dynamic, and it would be changing over the thousands of the years as the cosmic dance was reaching its climax. The collision would also be triggering the waves of the star formation throughout the merged galaxy, and it would be lighting up the night sky with the clusters of the newborn stars. From the ground, the heavens could be looking like a celebration in the slow motion, a grand display that was lasting far longer than any single human lifetime. But the possibility is remaining that no one will be being here to be seeing it, not even the microbes. The long-term habitability of the Earth is not being guaranteed, and in the deep future, the forces that are shaping the planets and the stars will not be waiting for us. The galaxy will be colliding, and the black holes will be merging, and the universe will be carrying on, whether the Earth is still being spinning or not. If the Earth does be remaining, then it will be bearing the silent witness to one of the most spectacular shows in the entire history of the cosmos. A front row seat to the day when the two galaxies are becoming one, and when the monster that is at the center of our own is finally meeting its match.